Hey everyone, I'm Morgan Willis, Principal Cloud Technologist at AWS, and I want to welcome you to this course. In this course, you will learn the key concepts behind cloud computing and explore AWS services using real-life examples covering compute, networking, storage, databases, security, and more. This course is intended for people working in IT or IT-related fields who have a general knowledge of IT topics but have yet to learn much about the AWS cloud. To kick off the course, we will cover the basics of what the cloud is, the benefits of the cloud, the AWS global infrastructure, and identity and access management. This will give you a solid foundation for learning the rest of the more technical topics contained in the course. Then we will focus on computing, and for this topic, we will dig into the services Amazon Elastic Compute Cloud, AWS container services like Amazon Elastic Container Service, and serverless compute options like AWS Lambda. Then we will discuss networking in AWS using services like Amazon Virtual Private Cloud and other networking technologies used for creating, securing, and connecting to your own private network in AWS. For storage, we'll explore how and when to use Amazon S3, Amazon Elastic Block Store, and others. For databases, we will cover many use cases around the different database services AWS has to offer, but with a special focus on Amazon Relational Database Service and Amazon DynamoDB. Then finally, we will discuss monitoring and scaling your application. For that, we'll use Amazon CloudWatch and Amazon EC2 auto-scaling alongside Elastic Load Balancing. We aren't going to focus on theory alone in this course. Instead, we will use a hands-on example through a cloud-based application that will build over the duration of the course piece by piece. The app we will build is an employee directory application that stores images and information about fictional employees in a company. There's no coding required for this course. You will have access to the source code if you want to explore it further. This course includes written segments we refer to as readings or notes to reinforce ideas, dive deeper into topics, as well as provide background information on concepts we did not cover in the videos. Because of this, I highly suggest that you take the time to complete all of the readings to get the full benefit of the course. So, again, welcome, and as we say at Amazon, work hard, have fun, and make history. Hey everyone, my name is Morgan Willis. I'm a Principal Cloud Technologist with AWS. What that means is I essentially build things, learn AWS, and then I get to share my knowledge with you all. I had a career in software development before I started working in training and certification here at AWS. I really love technology and have been in the field for over 10 years in roles from technical support to database administration to web application development. And while it's true that I do love technology, I also have a regular life outside of work where I'd like to hike in the beautiful sun, rain, sleet, or snow. I also like to ski and really enjoy just about any outdoor activity all seasons of the year. I'm looking forward to helping you navigate the world of AWS over the coming lessons. And this here is Meowsy. He's my trusted sidekick. He spends time with me while I type away on my computer, and I think he's picked up a thing or two over the years. His knowledge of AWS at this point is pretty great for a cat. I think I can even hear him sneaking on my computer in the middle of the night to build his own solutions on AWS. I have a feeling his knowledge will come in handy for this course. More on that later.
Hey y'all, I'm Seth. I'm a cloud technologist with AWS, and I've been working with the AWS cloud for close to 15 years. Like Morgan, I have spent most of that time learning, building, and sharing my knowledge with customers like yourself. In addition to my experience with AWS, I have worked in a variety of industries, and I've been on both the data center and the cloud side of infrastructures. Outside of my life in tech, I mostly enjoy spending time with friends, which primarily includes my 4-year-old wonder dog named Fluffy. Speaking of Fluffy, sometimes I think she knows more about AWS than she lets on. Every once in a while, I notice her drawing AWS architectures in a journal, and I wonder where she learned all of this. She can't bring me the ball back when we play fetch, but she always wags her tail when I mention cloud computing. I think Fluffy has something to say about cloud computing, so stay tuned for some of her helpful tips and tricks.
Hi there, my name is Morgan Willis, and I'm a Principal Cloud Technologist here at AWS. As you're working your way through the course, you may want to get in touch with the AWS community or reach out to the team who created this course. This video is to help you understand where to direct your questions. You may have questions about the AWS services you are learning about, or you might find that you have a specific question about something you are working on related to AWS. For these types of questions, I highly recommend you check out Repost. Repost can be found at the URL repost.aws, and this website gives you access to a vibrant community where you can ask AWS-related questions and get answers. Something to keep in mind about our courses is that AWS innovates at an extremely fast rate. This means that some of our content can get slightly out of date when new features are released or if the AWS console changes. If you see any out-of-date, incorrect, or broken content, you can contact us course creators directly by reporting the issue using the form that is included in the course materials following this video. An example of something you would use this form for is a hands-on tutorial or exercise that has instructions that are out of date or are no longer correct. If you have something go wrong within your AWS console while working through an exercise or lab, this is not something that you would enter a ticket for, as we will not have access to your specific AWS account. The ticket system is meant as a place to report issues with our courses. Finally, if you have a question about a course completion certificate or anything related to the learning platform you are taking this course on, please reach out to the learning platform to support and resolve these issues. I hope this helps you find the help you need. See you later. Hey there. I hope you're excited to learn about cloud computing on AWS. I'm excited to get started too, so let's hop in. To kick things off, we are going to cover some of the foundational concepts you'll need to know about when working with AWS. Working with AWS is part theory, part technical knowledge, part vocabulary, and lots of practice and experimentation. These first few lessons are going to help you establish a little bit from each of those categories. You will learn the theory behind cloud computing and the benefits of the cloud. This will help you make informed decisions about the cloud from a high level and give you some of the reasoning around why and when to use the cloud. Then we will dive into the AWS global infrastructure, covering regions and availability zones, followed by lessons on how to interact with AWS services. This lesson is going to give you the technical knowledge and vocabulary you need to create and discuss AWS architectures and properly understand AWS documentation and examples. A lot of what AWS offers can relate back to concepts used in traditional on-premises computing, and getting started with AWS means comparing these concepts to AWS concepts. After that, we will begin to discuss security and identity and access management. This is important to understand when you're getting started because as soon as you create an AWS account, you'll have some actionable knowledge on how to secure that account right from the start. Starting off secure is a good place to be. Throughout all the topics in these next few sections and over the duration of the entire course, we'll be using a sample employee directory web application to demonstrate how AWS services are used. Let's go ahead and take a look at the employee directory app. You can see I'm in the browser, and I want to show you the functionality. This is a basic CRUD app, or Create, Read, Update, Delete. This app keeps track of employees within a company, so the first thing I'm going to do is create a new employee. To create an employee, we'll give the employee a name, and I'm going to add myself, so I'll add my name. My location is USA, and then my job title, I'll enter in Cloud Technologist. And then we can add some badges for each employee. This is like an employee's flair. So I'm going to select Mac user for myself and photographer, and then I will click Save. Now I'm back on the homepage, and I actually forgot to add a photo for this employee. So let's go ahead and edit it and add the employee photo. You can also see this app gives me the ability to delete employees from the directory. So, those are the features of the app from a user's perspective. Time to review how we will build this app using AWS services. This application will be built in a private network using Amazon Virtual Private Cloud, or VPC. We will host the application's backend code on Amazon Elastic Compute Cloud, or EC2, which is a service that essentially offers virtual machines on AWS. So, let's go ahead and add those servers to our diagram. The employee data will be stored in a database, which will also live inside this network, and will be hosted using a service called Amazon Relational Database Service, or RDS. So I'll go ahead and add that to the diagram as well. The images for the employees will be stored using the Object Storage Service Amazon Simple Storage Service, or S3, which allows the unlimited storage of any type of file like images in our example. These are the basic building blocks of our application. We will use Amazon CloudWatch for monitoring the solution, and we will also want to ensure that our application is scalable and fault tolerant. So I'm going to go ahead and add Amazon Elastic Load Balancing and Amazon EC2 auto scaling to this diagram. For security and identity, we will be using Amazon Identity and Access Management, or IAM, so let's add that. There's a lot of pieces on this diagram, but don't worry, we will build this app step by step using the AWS Management Console. We will add to this diagram, reference it, and change it throughout the course to meet our needs and let it evolve as new ideas and techniques enter our world. One more thing to note about this course before I let you go. If you hear this noise, it means that you are going to be seeing one of our informational pop-ups on the screen, which convey extra information like word definitions, AWS best practices, tips, tricks, or general commentary written for you by our lively furry sidekicks, Meowsy and Fluffy. They know all the tips and are very helpful little friends to have around during this course. That's it for now. See you soon.
For our employee directory application, we'll be using photos of each of our employees. If we have only one copy of those photos and don't want to lose them, we have to store them somewhere safe. Currently, the only copy of these photos are saved on my laptop, but if my laptop breaks, what happens? No more photos. I want to make sure this doesn't happen, so I'm going to upload the photos to AWS to ensure that the copies exist even if my laptop is destroyed. This also allows me to access my photos from anywhere. My home, my phone, a plane, on a train, everywhere. When I store these photos in an AWS service, I'm storing it in a data center somewhere, on servers inside that data center. But if a natural disaster happens, such as an alien coming down from space and destroying a data center, then what do we do? Luckily, AWS has planned for this event, and many others, including natural disasters and other unavoidable alien accidents. The way they plan for it is through redundancy. AWS has clusters of data centers around the world. So here, AWS would have a second data center connected to the first through redundant high-speed and low-latency links. That way, if the first data center goes down, the second data center is still up and running. This cluster of data centers is called an availability zone, or AZ. An AZ consists of one or more data centers with redundant power, networking, and connectivity. Unfortunately, sometimes natural disasters like hurricanes or other disasters might also extend to impacting an entire AZ, but AWS has planned for that too, again using redundancy. Like data centers, AWS also clusters AZs together and also connects them with redundant high-speed and low-latency links. A cluster of AZs is simply called a region. In AWS, you get to choose the location of your resources by not only picking an AZ, but also choosing a region. Regions are generally named by location, so you can easily tell where they are. For example, I could put our employee photos in a region in Northern Virginia called the Northern Virginia region. So knowing there are many AWS regions around the world, how do you choose an AWS region? As a basic rule, there are 4 aspects you need to consider when deciding which AWS region to use: compliance, latency, price, and service availability. Let's start with compliance. Before any other factors, you must first look at your compliance requirements. You might find that your application, company, or country that you live in requires you to handle your data and IT resources in a certain way. Do you have a requirement that your data must live in the UK boundaries? Then you should choose the London region, full stop. None of the rest of the factors matter. Or if you operate in Canada, then you may be required to run inside the Canada Central region. But if you don't have a compliance or regulatory control dictating your region, then you can look at other factors. For example, our employee photos are not restricted by regulations, so I can continue looking at the next factor, which is latency. Latency is all about how close your IT resources are to your user base. If I want every employee around the world to be able to view the employee photos quickly, then I should place the infrastructure that hosts those photos close to my employees. We are all bound by the speed of light. Applied to your business, that means that if your users live in Oregon, then it makes sense to run your application in the Oregon region. You could run it in the Brazil region, but the latency from Oregon to Brazil might impact your users and create a slower load time. But maybe I really want to run my application or store my employee photos in Brazil. One problem I might run into is the pricing, which is the next factor we'll talk about. The pricing can vary from region to region, so it may be that some regions, like the Sao Paulo region, are more expensive than others due to different tax structures. So even if I wanted to store my employee photos in Brazil, it might not make sense from the latency perspective or the pricing perspective. And then finally, the fourth factor you'll want to consider is the services you want to use. Often, when we create new services or features in AWS, we don't roll those services to every region we have right away. Meaning, if you want to begin using a new service on day one after it launches, then you'll want to make sure it operates in the region that you're looking at running your infrastructure in. To recap, regions, availability zones, and data centers exist in a redundant, nested sort of way. There are data centers inside of availability zones and availability zones inside of regions. And how do you choose a region? By looking at compliance, latency, pricing, and service availability. Those are the basics, but it isn't the end of the story when it comes to AWS Global Infrastructure. We also have the Global Edge Network, which consists of edge locations and regional edge caches. Edge locations and regional edge caches are used to cache content closer to end users, thus reducing latency. Consider this scenario. You are a company hosting a website to your users all over the world. Even though your website is being downloaded from all over, it's hosted out of an AWS region in North America, say Ohio. Without caching, every user would need to send a request to the Ohio region where the data is downloaded, and then the data would be returned to the user and rendered in their browser. If the user is located in the USA or a nearby country, there may not be much latency in this process. However, if a user is coming from a place that is located far from the Ohio region, then latency will be greater. Latency is a big hurdle for many use cases, including web applications. So, to reduce this latency, you could use the edge locations to cache frequently accessed content. When you cache content at an edge location, a copy is hosted across the edge locations around the world. That way, when a user goes to retrieve that information, it will come from the closest edge location, which will greatly reduce the latency for that user. You can use services like Amazon CloudFront to cache content using the edge locations. When you own the infrastructure, it's easy to understand how you interact with it, because you can see it, touch it, and work with it on every level. If I have a server that I've stood up in my closet, interacting with that server is easy because it's mine. I can touch it. When I remove the ability for me to touch and see something, like when the infrastructure becomes virtual, the way that I work with that infrastructure has to change a bit. Instead of physically managing my infrastructure, now I logically manage it through the AWS Application Program Interface, or API. So now, when I create, delete, or change any AWS resource, whether it's a virtual server or a storage system for employee photos, I use API calls to AWS to do that. You can make these API calls in several ways, but the three main ways we're going to talk about in AWS are the AWS Management Console, the AWS Command Line Interface, and the AWS Software Development Kits, or SDKs. When people are first getting started with AWS, they typically use the AWS Management Console. This is a web-based method that you log into from your browser. The great thing about the console is that you can point and click. By simply clicking and following prompts, you can get started with some of these services without any previous knowledge of the service. With the console, there's no need to worry about scripting or finding the proper syntax. When you log into the console, the landing page will show you services you've recently worked with, But you can also choose to view all of the possible services organized into relevant categories such as compute, database, storage, and more. If I change the region to Paris, you're making requests to eus3.console.aws.amazon.com, or the Paris region's web console. After you work with the console for a while, you may want to move away from the manual creation of resources. For example, in the console, you have to go through multiple screens to set configurations to create a virtual machine. And if I wanted to create a second virtual machine, I would need to go through that process all over again. While this is helpful, it also leaves room for human error. I could easily miss a checkbox or misspell something, or even skip important settings by accident. So, when you get more familiar with AWS, or if you're working in a production environment that requires a degree of risk management, you should move to a tool that enables you to script or program these API calls. One of these tools is called the AWS Command Line Interface, or CLI. You can use this tool in a couple of ways. One is to download the tool and then use the terminal on your machine to create and configure AWS services. Another is to access the CLI through the use of AWS CloudTrail, which can be done through the console. With both of these options, instead of having a GUI like the console to interact with, you run create commands using a defined AWS syntax. For example, if I wanted to launch a virtual machine with the CLI through CloudTrail, I first use this quick shortcut to open a session. Once my session is started, I type in AWS, which is how we know we interact with the API. Then type in the service. In this case, it's EC2, the service that allows us to create and manage virtual machines, which we'll learn about later. And then the command that we want to perform in that service, and any other configurations we want to set. One command versus multiple screens you have to click through in the console can help reduce accidental human errors. But that also means you have to work with defined syntax and get that syntax correct in order for your command to run successfully. So there is some upfront cost in just understanding how to form commands, but after a while you can begin to script these commands out, making them repeatable, which can greatly improve efficiency in the long run. The other tool that allows you to interact with the AWS API programmatically is the AWS Software Development Kits, or SDKs. SDKs are created and maintained by AWS for the most popular programming languages such as Python, Java, Node.js, .NET, Ruby, and more. This comes in handy when you want to integrate your application source code with AWS services. For example, our employee directory application runs using Python and Flask. If I wanted to store all of the employee photos, including pictures of employees, in an AWS storage service, I could use the Python SDK to write code to interact with that AWS storage service. The ability of managing AWS services from a place where you can run source code with conditions, loops, arrays, lists, and other programming elements provides a lot of power and creativity. All right, that wraps this video up. To recap, you have three main options to connect with AWS: the console, the CLI, and the SDKs. In this course, we'll mainly be using the console to interact with the services, but feel free to challenge yourself by using the CLI if you're a bit more advanced.
In order to begin using AWS effectively, it's important to understand how security works in the cloud. You already know that by using AWS, you won't be managing every single aspect of hosting your solutions. You'll rely on AWS to manage portions of your workloads for you, taking care of that undifferentiated heavy lifting, like running the day-to-day operations of the data centers, and managing the various virtualization techniques employed to keep your AWS account isolated from, say, my AWS account. So the question is, who is ultimately responsible for security in AWS? Is it A, you, the customer, or B, AWS? The answer? Well, the correct answer is yes. Both you and AWS are responsible for securing your AWS environment. Let's explore this concept. AWS follows something called the shared responsibility model. We don't view solutions built on AWS as one singular thing to be secured. We see it as a collection of parts that build on each other. AWS is responsible for the security of some aspects. The others, you are responsible for their security. Together with both you and AWS following best practices, you have an environment that you can trust. Let's take a look at the shared responsibility model diagram. You can see we have the responsibility of security broken into two groupings, you and AWS each being responsible for different components. We describe AWS as being responsible for security of the cloud. For example, one piece of the puzzle for AWS is the AWS global infrastructure. And when I say global infrastructure, I mean the physical infrastructure that the cloud is running on. This is iron and concrete, buildings with fences protected by security guards and various other security measures. It also includes the AWS global backbone, or the private fiber cables that connect each AWS region to each other. Managing the security of these pieces is all on AWS. You don't need to worry about that as far as security goes. Then there is the infrastructure and various software components that run AWS services. This includes compute, databases, storage, and networking. AWS is responsible for securing these services from the host operating system up through the virtualization layer. For example, let's say you want to host some virtual machines or VMs on the cloud. We primarily use the service Amazon EC2 for this use case. When you create a VM using EC2, AWS manages the physical host the VM is placed on, as well as everything through the hypervisor level. If the host operating system or the hypervisor needs to be patched or updated, that is the responsibility of AWS. This is good news for you as the customer, as it greatly reduces the operational overhead in running a scalable and elastic solution leveraging virtualization. We will talk more about EC2 and elastic solutions in upcoming lessons. For now, let's get back to the security aspect. So, if AWS manages the underlying hardware up through the virtualization layer, then what are you responsible for? Well, you are responsible for security in the cloud. Similar to how a construction company builds a building, and it's on them to make sure that the building itself is stable and secure. Then you can rent out an apartment in that building. It's up to you to lock the door to your apartment. Security of the building and security in the building are two different elements. For security in the cloud, the base layer is secured by AWS. It's up to you to lock the door. So, for our EC2 example, you are responsible for tasks like patching the operating systems of your VMs, encrypting data in transit and at rest, configuring firewalls, and controlling who has access to these resources and how much access they have. The main thing to understand is that you own your data in AWS. You are ultimately responsible for ensuring that your data is encrypted, secure, and has proper access controls in place. In many cases, AWS services offer native features you can enable to achieve a secure solution. It's up to you to actually use them. In other cases, you may devise your own solutions to meet compliance and security standards for your specific industry or use case. So that's the shared responsibility model at a high level. I do want you to keep something in mind though. There is some amount of nuance you should understand as we move through the course regarding the shared responsibility model. Each AWS service is different and serves a different purpose and a different use case. Therefore, the shared responsibility model can vary from service to service as well. This is a good thing, as you get to decide how to build your solutions on AWS. When you create an AWS account, you sign up with an email address and you create a password. The email address you sign up with becomes the root user of the AWS account. This root user has unrestricted access to everything in your account in most cases. We will discuss in a later lesson what types of users can be restricted and how to do that, but for now, I want you to understand that when you log into your AWS account using an email address and password, it means you are logging in as the root user. This root user can do whatever they want in the account. It has all of the powers that can be had. And with great power comes great responsibility, or something like that. So, knowing that the root user is all-powerful, you should do everything you can do to make sure that no one can gain access to this root user. Let's say there's a nefarious actor of sorts, and they have an evil plan to log into your AWS account with your root user, gaining access to all of the powers and permissions, and they go and delete all of your valuable data and AWS resources, and in their place, they spin up a lovely and expensive cryptocurrency mining operation, leaving you with the bill and none of your data as they walk away with a full crypto wallet. Sounds less than ideal. Well, how can you prevent that from happening? You could, of course, create a hard-to-crack password, and that will give you some level of security. This, however, is an example of single-factor authentication, where all someone needs to do is match the password with the email address, and boom, they're in. We recommend as a best practice that right after you create your AWS account, you enable multi-factor authentication, or MFA, on the root user. MFA introduces an additional unique piece of information that you need to enter to gain access to the account. There are a variety of devices, virtual or physical, that generate one-time passwords that can be integrated with your AWS account for MFA. For example, I personally use a virtual MFA device that is an app on my phone. This app produces a string of numbers for one-time use that I type into the console after I log in using my email address and password. Even if someone guessed the password, they cannot gain access to the account without the numbers generated by the virtual MFA device. No matter what type of MFA device that you choose to use, and I will include a link to the supported devices in the readings for you to look into, the most important thing is that you are using MFA on the root user. That way, even if someone, the nefarious actor, cracks your password, they still cannot gain access to your account, all thanks to MFA. On top of enabling MFA for the root user, we strongly recommend that you do not use the root user for your everyday tasks, even the administrative ones. There are really only a few actions that require root user access. Coming up, you'll learn how to create an IAM user and use that to log into your AWS account instead of using the root user. Let's take a look at the application we are going to be building out throughout the course. We've already gone over the design of this application, and what I want to focus on now is access control. There are multiple places on this diagram where we can identify the need for access control and credential management. The first being that we need to manage how users log in and use the employee directory application. We could require that people have a valid credential, like a username and password, to log into the app. That is access management on the application level. Then there is the fact that we know the code running the employee directory application on a virtual machine being hosted by the service Amazon EC2, and that code will need to make API calls to the object storage service Amazon S3 in order to read and write data like images for the employees. Well, here's the thing. Just because both Amazon EC2 and Amazon S3 have existing resources in this account, it doesn't mean that the API calls made from the code running on the EC2 instance to S3 are automatically allowed to be made. In fact, all API calls in AWS must be both signed and authenticated in order to be allowed, no matter if the resources live in the same account or not. The application code running on the Amazon EC2 instance needs access to credentials to make the signed API call to Amazon S3. So that's another place with the need for a credential and access management. Now let's take this a step further. How are you going to build out this architecture? Well, you'll need access to an AWS account through the use of a login. Your identity within this AWS account will need permissions to be able to do things like create this network, launch the EC2 instances, and create the resources that will host and run the solution in AWS. Yet another place you need credentials. The root user, which you have already learned about in a previous lesson, has these permissions, but you don't want to be using the root user to administer your AWS resources. And let's assume you won't be the only one working on or building out this application. It's more likely that within one AWS account, there would be many people who need access to build and support your solutions. You'll have different groups of people responsible for different parts of the architecture. The people who would write and deploy the code might be software developers, whereas the people who would be responsible for making changes to, say, the network would be a different group of people. You wouldn't and shouldn't give everyone who needs access to the AWS account the root user credentials to log in. You instead would have unique credentials for each person logging in. This is where the service AWS Identity and Access Management comes in. We identified 3 places where we will need access and credential management. AWS Identity and Access Management, or IAM, can help take care of these 2 spots on the diagram. AWS IAM manages the login credentials and permissions to the AWS account, and it also can manage the credentials used to sign API calls made to AWS services. IAM would not, however, be responsible for application-level access management. The code running on this instance would use separate appropriate mechanisms for authenticating users into the application itself, not IAM. All right, so let's start with the AWS account level. IAM allows you to create users, and each individual person who needs access to your AWS account would have their own unique IAM user. Creating users for everyone who needs access to the account takes care of authentication. Authentication being verifying if someone is who they say they are because they had the proper credentials to log in. Now it's time to introduce authorization. Authorization is this. Let's say you've logged in and you are who you say you are. You've been authenticated. Now you want to create resources and manage AWS resources, like create an Amazon EC2 instance, for example. Sure, you've logged in, but do you have the correct permissions to be able to complete that action? The idea that your permissions control what you can or cannot do is authorization. Are you authorized to launch an EC2 instance? IAM users take care of authentication, and you can take care of authorization by attaching IAM policies to users in order to grant or deny permission to specific actions within an AWS account. Keep in mind, when I say action here, I'm referring to an AWS API call. Everything in AWS is an API call. IAM policies are JSON-based documents. Let's take a look at an example. This IAM policy document contains permissions that allow the identity to which it's attached to perform any EC2-related action. The structure of an IAM policy has an effect, which is either allow or deny. An action, which is the AWS API call. In this case, we have EC2:*, which includes all EC2-related actions. You can restrict this to be specific API calls. For example, I can restrict this action to be just run instances, and then any user with this policy attached would only be allowed to run EC2 instances, but perform no other EC2-related tasks. IAM lets you get very granular with your permissions in that way. Continuing with this example, we see the resource, which allows you to restrict which AWS resources the actions are allowed to be performed against. You can also include conditions in your policies that can further restrict actions. IAM policies can also be attached to groups. IAM groups are very simply just groupings of IAM users. You can attach a policy to a specific user or a group. When you attach a policy to a group, any users that are a part of that group would inherit the permissions. We recommend that as a best practice, you organize users into groups and assign permissions to groups instead of individual users where possible. This makes it easier to manage when people change job roles or multiple users need permissions applied or revoked. Another best practice to follow is that we recommend when you create your AWS account, you set up MFA for the root user, then create an IAM user with admin permissions. Log out of the root user and then log in with the IAM user that you just created. From there, you can use this user to create the rest of the IAM groups, users, and policies. The reason we suggest you do this is because you cannot apply a policy to the root user, but you can to an IAM user. Now that I've told you about IAM users, groups, and policies, we've addressed this part of access management that we needed for our application. But what about this part? The EC2 instance needs credentials to be able to make the signed API call to S3 for reading and writing employee images. Am I suggesting that you make an IAM user with a username and password for the application running on EC2 to use? No, I am not. This is where role-based access comes into the picture. Coming up, we will learn about the temporary access that IAM roles provide and how it can apply to this use case here. All right, so you've learned about IAM users, groups, and policies. Policies can be applied to AWS identities like users and groups to assign permissions. They also, however, can be applied to another AWS identity, IAM roles. An IAM role is an identity that can be assumed by someone or something who needs temporary access to AWS credentials. Let's dive into what I mean when I say AWS credentials. Most AWS API calls that are made must be signed and authenticated, but how does that process work? When you send HTTP requests to AWS, you must sign the request. This signing process happens programmatically and allows AWS to verify your identity when a request is made and run through various security processes to ensure a request is legit. IAM users have associated credentials like an access key ID and secret access key that are used to sign requests. However, with regards to our architecture, the code running on the EC2 instance needs to sign the request sent to S3. I already told you that I don't intend for you to create an IAM user with credentials to be used by this app. So how will the application gain access to the needed AWS Access Key ID and AWS Secret Access Key to sign the API call? The answer is IAM roles. IAM roles are identities in AWS that, like an IAM user, also have associated AWS credentials used to sign requests. However, IAM users have usernames and passwords as well as static credentials, whereas IAM roles do not have any login credentials like a username and password, and the credentials used to sign requests are programmatically acquired, temporary in nature, and automatically rotated. In our example, the EC2 instance will be assigned an IAM role. This role can then be assumed by the application running on the virtual machine to gain access to its temporary credentials to sign the AWS API calls being made. A role can be assumed by many different identities, and they have many use cases. The important thing to know about roles is that the credentials they provide expire, and roles are assumed programmatically. To get an idea of this, let's create a role using the AWS console. I'm already logged in and will navigate to the IAM service. Now I want to create the role the EC2 instance is going to use for the employee directory application. Now we will click Roles in the left-hand side and select Create Role. We will then select the trusted entity this role is intended to be used for, and in our case, this will be EC2. Then we will click Next. Now we get to select the permissions assigned to this role. Again, permissions being what actions does this identity have the authority to take. We want this identity to be able to read and write to Amazon S3, so I will search for S3, and you can see there are multiple options here for pre-written policies that I can choose from. I also can write my own custom policy, which would also show up here if I created it ahead of time. I'm going to select S3 full access for the policy. In the real world, you would choose a more restrictive IAM policy for this, but for a proof of concept like this course is intended to provide, we will leave the permissions a bit looser for now. You would come back and change the permissions attached to this role to be more granular if this were ever to make it to a production type environment. Now we also need to add another permission here, and that's for DynamoDB. So I will exit out of the S3 filter and then type in DynamoDB and hit enter. And then we will select the Amazon DynamoDB full access permission. Then we will click Next. Then we can give this role a name, which is Employee Web App Role. Then we can scroll down and we can click Create Role. We can see that this role has now been created successfully. And if we click on the role and scroll down, we can then see that this role has 2 permissions attached. It's very common for roles to be used for access between AWS services. Just because 2 resources exist in the same AWS account, it doesn't mean that they can send any API calls to each other. If one AWS service needs to send an API call to another AWS service, it would most likely use role-based access, where the AWS service assumes a role, gains access to temporary credentials, and then sends the API call to the other AWS services who then verifies the request. Another identity that can assume an IAM role to gain access to AWS is external identity providers. For example, let's say you have a business that employs 5,000 technical employees that all need access to AWS accounts. You already have an identity provider system in place that allows these employees to log into their laptops and gain access to various corporate resources. Should you also now go create 5,000 IAM users for these employees to access AWS? Well, that doesn't sound very efficient. You instead can leverage IAM roles to grant access to existing identities from your enterprise user directory. These are known as federated users. AWS assigns a role to a federated user when access is requested through an identity provider. We also have AWS services that can make this process easier, such as AWS IAM Identity Center. These are a couple of examples of role-based access in AWS, and this is just the introduction. Check out the class readings for more information, and don't worry if you don't quite grasp this concept yet, as we will continue using roles in our demos and examples throughout this course. It's time for a hands-on lab. At this point, you've learned about some of the best practices for securing AWS accounts using AWS IAM, so let's go ahead and put those best practices into practice. In this lab, you will access the IAM dashboard and explore existing groups, users, roles, and policies that will be preloaded into the exercise environment. You will learn how to manage users and groups by performing tasks like adding users to groups and allowing users to inherit specific group permissions. You also will learn about how permissions work with AWS by exploring different AWS services using different IAM users. That's all for this lab. Throughout the course, there will be more labs that will loosely follow along with what we do in the videos. Have fun and see you in a bit. Hello everyone. In this video, we are going to create the IAM role for our employee directory application, and we will also look at how to create users and look at the different AWS access keys, which are used for programmatic access to AWS APIs. So to start off, let's create the role for our application by selecting Roles in the left-hand navigation of the IAM dashboard, and then we will click Create Role. On this page, we need to select what the trusted entity type is to assume this role. We know that roles allow you to get access to temporary credentials that are used to make calls to AWS API calls. You want to make sure that you're restricting who can assume this role. Not anyone can assume this role, right? So under the trusted entity type, we have the AWS service. An AWS service, that would be something like an EC2 instance, a Lambda function, other services that are assuming a role to make AWS API calls. You could have an AWS account. This would allow you to allow cross-account access to permissions for resources in your account. You also could select a web identity, which would allow for federated users to assume a role. You have a SAML 2.0 federation. So if you have a corporate directory that is on premises that would be using SAML, you could use this as your trusted entity type, or you could create a custom trust policy. We're going to select AWS service for this, and then we're going to select EC2 since our employee directory application will be running on EC2. Next, we can select the next button, and then we're brought to the page to add permissions. This lists out the different permissions policies that are in IAM, and right now it's pulling back the AWS managed policies that exist in this account by default. And what a managed policy is it is a policy that is created and managed by AWS. And so what I mean by that is let's go ahead and look at a policy for S3. So if I type in S3 in the search bar and then hit enter, I'm going to expand this Amazon S3 full access policy. And we can see the JSON, which is the permissions for this policy. We can see we have the effect is allow. That's either going to be allow or deny. There's no other option besides allow or deny. And then there's the action, which is going to define what AWS API calls are allowed to be made. So we can see that we have S3:* and S3 object lambda:*. That's a wildcard to determine all API calls are allowed against this service. And then we also have the resource here, which is also set to star. So this would be all S3 resources. This is a very permissive policy. In the real world, you would likely want to change this to allow just the API calls that your application needs, nothing more, and just the resources that you intend to have this policy be related to. So to do that, you would have to create a custom policy. So if I scroll up, you could click on this custom policy button, which would take you to a new page where you could then create your custom policy. For now, we're going to use the AWS managed policies, and I'm going to select the checkbox for Amazon S3 full access. And then I'm also going to type in DynamoDB and exit out of the S3 filter, and then select the Amazon DynamoDB full access policy here as well, because later in the course, we are going to be using DynamoDB as the database for this application. So to prepare the role, I've selected both the S3 full access and DynamoDB full access. Now we'll click next. Then we can give this a name. I'm going to name this Employee Web App. And then I'm going to scroll down. We can view the trusted entities here. So this is our trust policy. We're allowing the API call STS assume role. And who's allowed to assume this role? ec2.amazonaws.com. So an EC2 instance is going to be allowed to assume this role only. All right, so now I can scroll down and then click create role. Once your role is created, you can then click on the role, which will bring you to the page where you can see the information about this role, such as the ARN, the Amazon resource name, and you can also scroll down. You can view the permissions attached. You could add new permissions if you want to. You can simulate the permissions. You can view the trust relationships. You can also view any tags associated with this, which are key value pairs. So this is where you can get all of the information about your role and where you can manage your role. So next, what I want to do is create a user. So I'm going to click on users in the left-hand navigation. Then I'm going to click add users, and let's give this user a name. Let's say it's EC2 admin. And then I want to click the checkbox for enabling console access. So what that means is I want to allow this user to be able to sign in to the AWS Management Console. So note, by default, this was unchecked, meaning that just because you create a user doesn't mean they have access to the console. I'm going to go ahead and check this. And then I'm going to allow an auto-generated password to be created. And then I want to leave the checkbox checked for users to create a password at the next sign-in. So this will allow them to change their password once they log in for the first time. Now we'll click next. And next, what I want to do is I'm going to add the users to a group. We currently don't have any groups, so I'm going to go ahead and click create group. And then what I want to do is add a group name. Let's say this is EC2 admins. And then I want to attach a policy to this group because we know that it's a best practice to attach policies to groups, not to users directly. So I'm going to select the Amazon EC2 full access policy, and then I'm going to scroll down and click create user group. And now I can select this user group to add this user into, and then I can click next. And then we can scroll down. We can see the permissions that this one user currently has. It will be inheriting the permissions from the EC2 admins group. And then it also has directly attached to it the IAM user change password permission, which will allow this user to change their password. So now we can click create user. And now we can go ahead and click return to users list. We didn't download the password for this. That's fine. I don't intend to actually use this user. It's just for demonstration purposes. So we'll click continue. And now if I click on this user, what I want to do next is click on the security credentials tab. And if we scroll down, you can see that we have this panel here called access keys. Access keys are going to allow your users to make programmatic calls to AWS using things like the AWS command line, the AWS software development kits, where maybe they're developing locally on their laptop and they need their code to be able to reach out to AWS. So I'm going to go ahead and create an access key here. And then I want to use this for the command line. And then I'm going to go ahead and click the checkbox for I understand the above recommendation. What this is saying is it's saying, hey, there's another service in the browser that you could use to use the AWS CLI called AWS CloudTrail. We're going to go ahead and create the access keys anyways. I'm going to select this checkbox and then click next. And then I'm going to click next again and click the create access key. All right, so here you can see we have our access key here. And then we have our secret access key, which is not being shown currently on this page, but you could click show and then copy it. And you would use this access key and secret access key to be able to configure your command line locally. Now I'll click done and then click continue. So now for a little bit of cleanup, I'm going to select actions and then I'm going to click deactivate and then deactivate. And then I will click actions and then delete. And then we can copy and paste the access key ID here and then click delete. All right, that's it for this video. Hopefully you know a little bit more about roles and users. All right, you've learned some AWS vocabulary, some of the concepts behind cloud computing, as well as some of the specifics around cloud identity and access management. As a refresher, let's take a look at the architecture diagram we'll be building out. you'll remember that it's fairly complicated at a glance. There are many different services working together to host this solution, and to get this entire thing built out this way will take some time and understanding. You'll get the opportunity to see how each piece is built throughout the upcoming lessons. What I want to do now is show you how we are going to host our employee directory application using a service called Amazon EC2, which has been mentioned in previous videos. I find that the best way for me to explain to you how these services work is to show you how they work. So, what we are going to do is we are going to call Ceph in here to launch an Amazon EC2 instance and host the employee directory application using the defaults provided by AWS. AWS provides you with something called a default VPC, which is a private network for your AWS resources. Every EC2 instance you launch using AWS must live inside of a network. So in order to complete this demo with the limited amount of information that we have shown you about AWS services, we will be using the default network provided by AWS, and we will accept most of the default values for launching an EC2 instance. Let's bring Ceph in for some help with this one. Hey, Ceph.
Hey Morgan, is it time to launch our first EC2 instance?
It is. We'll be using the default VPC to launch this first instance, and we will configure the bare minimum to get our application up and running. Sound good?
Yep, I got it. Let's get started. I'm already in the EC2 management console, and I will navigate to the service Amazon EC2. As Morgan already mentioned, Amazon EC2 is a compute service that allows you to host virtual machines. You'll learn a lot about this topic coming up soon, but for now, we are going to simply create an EC2 instance to try and help you wrap your mind around using AWS services on demand. From here, we'll launch a new EC2 instance. An instance is just what we call one single virtual machine. Now we have to select the configurations for this EC2 instance. You will go over these configurations in detail later. We can give this instance a name. I'll call it Employee Web App, and then we will select the free tier eligible options using a Linux AMI or Amazon machine image. And then scrolling down to the next section, we will select the free tier eligible T2 Micro for the instance type. Next, we normally need to select a key pair. This would be used to SSH into the instance. But we won't need to do this, so I'm going to select Proceed without a key pair and continue scrolling to the network settings. Here, we will select the network, so looking at network settings, we will click Edit. Then we can select the VPC and subnet for this instance, and as we discussed earlier, we will use the default VPC and leave the subnet at No Preference. The default VPC has configurations in place that make this experimentation process a lot easier when you're first getting started with AWS. Again, we will define all of these things later. Continuing on with network settings, we will create a new security group, which is an instance-level firewall that will allow HTTP and HTTPS traffic in to reach the instance. So we will add inbound rules for both of those. Now we will scroll down and expand Advanced Details. We will accept most of the defaults here except the IAM instance profile and user data, which we will provide a value for. For the IAM instance profile, we will use the IAM role that will be used by the application, though this won't come into play until later when we have our S3 bucket created. But for now, let's click the dropdown and select that IAM role. Now, scrolling down to the user data, this is a script that is going to run when the instance boots up. Let's go ahead and paste in our user data script. This script will download the source code for the app, start the web server, and kick off the application code so it's ready to start handling requests. While you could have launched the instance, then connected to it via SSH, configured and started your application manually, we have decided to use a script to automate this process on launch. All right, now we can click Launch Instance. It can take a few minutes for the instance to boot up, so let's wait for that. And now it's up and running. To access the instance, copy the IP address from the details listed below, paste it into a new browser tab, And there you go. It's up and ready to go. Morgan, what do you think?
That looked great. It's exactly what I would expect at this point because there is no data being served from a database. So I expect to see just a home page with no info. So that's great. Thank you, Seth, for walking us through that. In upcoming lessons, we will discuss the specifics of not only EC2, but also networking on AWS, and you'll understand how everything we just kind of glossed over actually works. So stay tuned. Hey everyone, and welcome back. So far, you've been learning all about some higher level concepts regarding AWS, making sure you understand AWS in general, the global infrastructure, as well as setting up an account and providing yourself the right level of permissions. But you may also remember that we ended the last lesson by launching an EC2 instance to host our application. An EC2 instance is simply just a form of compute, meaning it gives our application power in the form of CPU, memory, and networking capacity so that we can process our users' requests. This concept of compute leads us into the next lesson, where we discuss your compute options on AWS. Of course, you've already seen one of these options, EC2, but we'll also discuss other common solutions such as container services like Amazon Elastic Container Service, or ECS, and Amazon Elastic Kubernetes Service, or EKS, as well as serverless options like AWS Lambda. After the upcoming lessons, you'll not only understand each of these compute services, but you'll also be able to compare them to one another. That way, you'll know how and when to apply each service to different use cases. You'll get an opportunity to see more demos with Amazon EC2, and we will go further into the details throughout this week. But as you imagine, we can't just launch this EC2 instance into space, right? We have to put it somewhere. And where do we put it? Well, we put it in a network that we'll need to customize for our application. Every EC2 instance needs to exist inside of a network, and on AWS, those networks are called VPCs. We'll learn all about networking on AWS using VPCs, but rest assured, this won't be too hard. We'll give you all the information you need to launch an EC2 instance into a VPC. All right, so that's what is on deck. Also, make sure you are checking out the readings that follow the videos. There's additional information in those readings that you won't see in the videos, like use cases, features we didn't have time to cover, and more. All right, I think that it's time for us to get started. Enjoy the lessons, and I will see you soon. Let's talk about compute. Every business needs raw compute capacity to run applications. These applications could be web servers, batch jobs, databases, HR software, machine learning, or just about whatever you can think of. The time, money, and effort it takes to get up and running with on-premises computing resources are fairly high. When you own your own fleet of physical servers, you first have to do a bunch of research to see what type of servers you want to buy and how many you need to buy. Then you need to purchase that hardware upfront. You'll wait multiple weeks or months for servers to be delivered. You then take them to a data center space that you own or rent to install them, rack and stack them, and wire them all up. Then you make sure the servers are secured, powered up, and ready to be used. Only then can you begin to host your applications on top of these servers. The worst part is, once you buy these servers, you are stuck with them, whether you use them or not. It's not easy to just suddenly provision more physical compute capacity when you need it, and it's even harder to get your money back on servers you no longer need. It's impossible to get the time back. Following a compute as a service model is much easier to get started and support operations over time. AWS took care of the hard part for you already as far as getting started goes. AWS already built and secured the data centers. AWS has already bought the servers, racked them and stacked them, and they are already online, ready to be used. In a previous lesson, we showed you how to launch the employee directory application with Amazon EC2. We didn't really talk about the details, how EC2 works, what configurations exist for it, and we definitely didn't discuss any other compute options that exist on AWS. AWS has different services for different use cases, and Amazon EC2 is one of the basic AWS services that are important to understand. We will be spending most of our time in these upcoming lessons exploring EC2. That being said, though virtual machines like EC2 are great, there are other compute services out there too, like container services and serverless compute. You'll learn about these other compute options and their use cases. Don't always assume that VMs are the default answer. Sometimes it makes sense to architect applications for serverless compute or containers from the start, depending on what you are building and what you are optimizing for. EC2 instances give you a lot of flexibility and control in the cloud, and you configure them to meet your needs. You can provision one or many instances easily, and at the end of the billing cycle, you only pay for what you use, either per second or per hour, depending on the type of the instance. When you no longer need an instance, you can terminate or stop the instance, and you will stop incurring charges. Not all servers are the same, and you are probably looking to run a specific type of operating system on your EC2 instance. AWS supports a range of operating systems, including Linux, macOS, Ubuntu, Windows, and more. To select the operating system for your server, you must choose an Amazon Machine Image or an AMI. The AMI contains information about how you want your instance to be configured, including the operating system, possible applications to be pre-installed on that instance upon launch, and other configurations. You can launch one or many instances from a single AMI, which would create multiple instances that all have the same configurations. Some AMIs are provided by AWS, whereas others are provided by the community and can be found using the AWS Marketplace, or you can build your own custom AMIs as needed. For example, Amazon Linux 2 is the AMI we selected when we launched our employee directory application. This AMI is provided by AWS, and it's essentially a pre-built EC2 optimized Linux image that has long-term support provided by AWS. Beyond the properties determined by the AMI, you can also configure the instance type and size, which correspond to the amount of compute, memory, and network capabilities available per instance. Different applications have different hardware requirements, and choosing the instance type for your application gives you the ability to pick the hardware that it runs on. It's also really nice that you have a wide variety of choices, as it's hard to achieve that same level of variety with on-premises resources. The instance types you can choose from are grouped for use cases like compute optimized, memory optimized, storage optimized instances, and more. There is a list of instance types you can find in the AWS documentation, and you can expect this page to be updated regularly as new instance types are released. For example, the G instance family are optimized for graphics-intensive applications, which would work best for use cases such as 3D visualizations or video encoding, whereas the M5 general-purpose EC2 instance family provides a balance of resources and are great for applications that use these resources in equal proportions, like web servers, our employee directory application example, or code repositories. When you are launching an EC2 instance, you will see something like this when selecting an instance type and size. The T3 or A1 is the instance type that determines the blend of hardware capabilities, then the dot, then the size, like small, medium, large. It goes down to nano and up to many, many extra large sizes. The great thing about this type of selection existing right at your fingertips is that you are no longer locked into hardware decisions up front. You can choose an initial EC2 instance type, evaluate its performance for your specific use case, and then later change it to a different type that is better suited for the application. EC2 is also resizable with a few clicks in the console, or can be done programmatically through an API call. All of these configurations being available to you via API enables you to embrace change over time easily as your workloads mature and change. So, okay, virtual machines are cool and totally not new, so how exactly does this impact your business? Well, the important thing is this: the flexible and low-cost nature of EC2 instances, as well as the ease of provisioning servers, allows for programmers and businesses to innovate more quickly by spinning up servers for a short amount of time to run experiments and find optimal configurations for your applications. EC2 offers a wide variety of hardware options to choose from, so you can optimize your solutions by selecting the right EC2 instance type for your application. And then you can optimize even further by right-sizing the resource, or selecting an instance size that is appropriate for your application and not over-provisioning like is often done on-premises. This type of optimization is hard to achieve on your own because with traditional on-premises deployments, you are working with hardware constraints that simply don't exist in the same way with the cloud. The ability to adapt to changes and choose really specific configurations for your virtual machines all through a couple of API calls is very powerful. And EC2 is really just the beginning of the story. One of the main reasons why EC2 provides so much value is the fact that you can provision new EC2 instances on demand, and just as easily you can get rid of instances that you no longer need. In most cases, you only get charged for instances that are currently running. EC2 allows you to stop and start instances at will, which enables you to treat your fleet of EC2 instances as elastic, scaling them in or out. Then at the end of the billing cycle, you only pay for what you use. We are building up to the idea of scaling your fleet of EC2 instances in and out to serve demand. But before we get there, it's important to understand some of the more basic things about EC2. Let's talk about the EC2 instance lifecycle. An Amazon EC2 instance transitions through different states from the moment you launch it through to its termination. You launch an EC2 instance from an AMI, and as you learned in a previous lesson, once the EC2 instance is launched, it enters a pending state. This state is essentially your VM booting up. Once the instance is ready for use, it enters the running state. In the running state, you will be charged for the EC2 instance. From running, you have a couple of different options. You can reboot the instance, which is similar to rebooting, say, your laptop. It turns off, then it turns back on again. Pretty straightforward. You can also choose to stop your instance. It will enter a stopping phase, then enter the stopped phase. Stopping an instance is like powering down your laptop. You can always turn it back on, and it will go through its usual boot sequence, moving through the pending state and back to the running state. The other option, which is similar to stop, is to stop hibernate your instance. This also enters the stopping phase and then the stopped phase. You can compare this to how you lock your laptop and shut the lid, but when you open it back up, everything is still in place where you left it. No boot sequence required. You are back up and running after a couple of seconds of the computer waking up. Since the state of the machine was written to memory when you stopped it, the state of the machine can be drawn from memory and put back into place. Then you're back up and running. Now, the last option depicted here is the terminate option. When you terminate an instance, it enters the shutting down phase, then the terminated phase. Terminating an EC2 instance is like taking your laptop out for a long boat ride off the coast and throwing it into the ocean, getting rid of it forever. It's now lost in the great blue sea. There is no hope of finding your laptop on an island shipwrecked one day, having been saved after spelling SOS in the sand. Anyways, I hope you had any data or state stored on that instance backed up, because once you terminate an instance, it's gone. That being said, there is a feature called termination protection that you can enable if you're worried about instances being terminated accidentally. You also will learn about persistent storage and EC2 in future lessons, so don't fret. We will show you ways you can make sure your data sticks around, even if the EC2 instance doesn't. So that is the EC2 instance lifecycle. It's definitely a good idea to remember how all of this works if you plan on using EC2 to host your applications. And don't think of terminating instances as a bad thing. If your EC2 instance is having technical trouble for one reason or another, maybe it needs an update or a patch, instead of logging into the instance to fix it or install software, you can launch a new one with the new changes in its place, and then you could terminate the old instance, having the new instance take that place. You of course can do in-place updates as well, but just know that you have the option to decide how to handle these sorts of tasks. You can launch or terminate EC2 instances to meet demand. So as demand for your application increases, you can launch more instances, and as it decreases, you can terminate instances. This keeps your EC2 instance fleet in line with demand. So again, terminating an instance isn't a bad thing and shouldn't be feared. Now, let's discuss the cost aspect of this. You only get charged for an EC2 instance if you're in the running state, or if you are in the stopping state when preparing to hibernate. This means that you can stop instances when they aren't in use. Say if you have applications that are only used during the work week. Run them when your employees are clocked in, and then stop them when they aren't. Remember, you can always start from a stop state, allowing them to resume working when necessary. Hello everyone. In this video, we are going to launch the Employee Directory application on an Amazon EC2 instance using the default VPC. So you can see I'm already in the AWS console, and I'm going to navigate to the EC2 dashboard. From here, I want to launch a new instance. So I'm going to select Launch Instance and then select Launch Instance again. And now this brings us to a page where we can provide the configurations for our EC2 instance. I'm going to give this a name. employee directory app, and then we can scroll down and we can view what AMI we want to choose. The AMI is the Amazon Machine Image, and this is a template that contains the software configuration for your instance on boot, like the operating system, any sort of application server, or any applications that you want to have pre-installed when you launch your instance. We're going to be using the Amazon Linux 2023 AMI for this, though you could browse the AWS Marketplace to get access to the different types of AMIs that vendors offer. So if you're using some sort of third-party software that you want to launch on an EC2 instance, they might have an AMI out there that you could use to make your life a little bit simpler. You also can create and manage your own AMIs and share them internally within your organization to say you can only launch an EC2 instance using one of our approved AMIs that might have some specific security or compliance sort of packages pre-installed. That's another option. So leaving the Amazon Linux 2023 AMI selected, I'm going to scroll down, and then we can select our instance type. The instance type will determine how much CPU, how much memory, what types of hardware is available to you on this instance. Some instances come with a GPU, for example. In this case, we're going to use the free tier eligible EC2 instance type, T2 Micro, which is the default that's selected. So we'll leave that the way it is. Then we can scroll down and select whether we want to use a key pair. The key pair is going to allow you to have access to this instance doing something like SSH. I'm going to select proceed without a key pair because if I need to connect to this instance, I'm going to use the connect button in the AWS console where I don't need to have a key pair to connect to this instance to view things like logs. Then scrolling down some more, we then can configure our network settings. This is using a default VPC and a default subnet. This default VPC is going to have subnets that have internet access, so meaning that there is an internet gateway attached to this VPC that allows internet traffic to flow into this default VPC. You'll learn more about VPCs coming up, but just understand that this default VPC does allow public internet access, which is good for our use case, but might not be great for other use cases where you would more than likely put your instance behind something like a load balancer, and then you would use private subnets. But we want to be able to access this instance directly. So with that in mind, we're going to use the default VPC, and we're also going to leave this auto-assign public IP to enable. And this will allow our EC2 instance to have a publicly reachable IP address once it's been launched. Then scrolling down a little bit more, we have to configure our firewall. This is going to be our security group. Security groups are instance level firewalls. We want to disable traffic from SSH because we're not going to need that. Then we're going to allow HTTPS and allow HTTP. In our application, we're going to be using HTTP directly. Then scrolling down, we can configure some storage. We're going to leave our root volume here, but we're not going to add any more EBS volumes. Then we can expand the advanced details section, and then we need to select an IAM instance profile. In this case, I'll be selecting the employee web app role, and this role has permissions attached to it to allow whoever's using the role to make calls to S3 or to DynamoDB. We know that our application has some code that's running that's going to be making API calls to S3 and DynamoDB. We need to allow our AWS SDK to actually get access to these credentials. And the way that we do that is through this IAM instance profile. So we're associating this role with this instance profile that will allow our code to get access to these temporary credentials. Then scrolling down some more, we will come to the user data section. And this is where you can provide a bash script that will run on launch. So this script here is what's going to be used to download and install our application. Our application was written in Python using Flask as the web server, and this is going to be for our employee directory application. So in the first line, we are just declaring that this is a bash script. Then we are using wget to download a zip file from S3. So we hosted this zip file in an S3 bucket for this to be downloaded. Then we're unzipping that, and then we're changing directories into that new directory. Then we're using yum to install Python 3 and pip. Then we're using pip to install any dependencies for our Flask application, which will all be listed in a file called requirements.txt, which got downloaded from this zip file. Then we're installing a package called stress. This stress package is going to be used to simulate a CPU spike on this instance, which is going to allow us to simulate auto-scaling whenever we use Amazon EC2 auto-scaling in a future lesson. Then we have 3 different environment variables, one for our photos bucket. We're going to be using S3 to store our photos. We don't have that value yet, so we'll just leave this placeholder there. Then we have the default region. We're operating out of Oregon. And then we have our Dynamo mode on, and this means that we want our application to use DynamoDB. And then we're running this application and hosting it on port 80. Now we can select Launch Instance, and this will begin to go build out the different things that we need, like our security group, and we can see that our instance has launched. Now, if I select this instance ID, that brings us to a page where we can then select our instance and view some information about it. We can see things like our public IP address, our private IP address, and our public DNS name, but we can't access this directly yet. We can see that our instance state is running, but if I refresh this, you can see that we have some status checks that are still initializing. I want to wait until both of these status checks have passed, so we'll give this a few minutes and then we'll come back once it's ready. Okay, we're back and we can see that our instance state is running and the status checks have passed. Now, if I select this instance again, we can then open up our IP address in a new tab. All right, and we can see that our employee directory application has been opened in a new tab and we have an empty employee directory. This is exactly what we would expect at this point, as we don't have a place to store our photos or the employee information with our S3 bucket or DynamoDB table. We're going to look at how to build out a custom network for this, the S3 bucket, and the DynamoDB table, and make all of this highly available in an upcoming lesson, so stay tuned. EC2 is great for all sorts of different use cases, from running basic web servers to running high-performance computing clusters. That being said, though EC2 is incredibly flexible, reliable, and scalable, depending on your use case, you might be looking at alternatives for your compute capacity. For example, let's say you are looking for a way to run containers at scale on AWS. Containers can provide you with efficiency and portability. In this context, I am specifically referring to containers like Docker containers or containers that use the containered runtime. If you aren't sure what containers are, please review the readings on containers. Containers are portable because everything an application needs to run, including the application code, dependencies, and configuration, are all packaged up together as one executable, which is the container itself. Since everything is self-contained, it means that you can expect your containers to behave the same way across different environments like development, QA, and production. AWS offers container services like Amazon Elastic Container Service, otherwise known as ECS, or Amazon Elastic Kubernetes Service, otherwise known as EKS. Both of these services are container orchestration tools. When you use containers on AWS, you need processes to start, stop, restart, and monitor containers running across not just one EC2 instance, but a number of them together called a cluster. The process of doing these tasks is called container orchestration, and turns out it's really hard to do on your own. If you have a few containers, it's not so bad, but once you get to hundreds or thousands of containers you are managing, it can be quite complex. Orchestration tools were created to help you run and manage containers. ECS is designed to help you run your containerized applications at scale without the hassle of managing your own container orchestration software. EKS does essentially the same thing but uses different tooling with different features. We aren't going to go too much into this now. However, I did include a link to more learning resources around containerized applications on AWS in the readings following this video. The way you can interact with these container services is you manage the containers running on a cluster through the Orchestration Tools API, and then the orchestration tool carries out the management tasks. You can automate scaling of your cluster hosting your containers, as well as automate scaling of the containers themselves. Containers have a shorter boot up time when compared to virtual machines. So if you need super fast response to increasing demand, then containers might be the service for you. Personally, I think the portability aspect that containers give are my favorite benefit of containerized applications. So you can choose to host containers on top of a cluster of EC2 instances as your hosting options, either for ECS or EKS. However, what if you were looking for an alternative to hosting your containers? Because you either don't need access to the underlying OS or you don't want to manage those EC2 instances. Well, you can use a compute platform called AWS Fargate, which handles most of the underlying details for you. Fargate is a serverless compute platform for ECS and EKS, and we'll talk more about what serverless is coming up next. When using Amazon EC2 or container services running on top of EC2 as a compute platform, you are required to set up and manage your fleet of instances. This means that you are responsible for patching your instances when new software packages or security updates come out, setting up the scaling of those instances, as well as ensuring that you've architected your solutions to be hosted in a highly available manner, which means deploying instances across 2 AZs at a minimum, as we discussed earlier. This is less management and operational overhead than you would have if you hosted the same solutions on premises, but management processes will still need to be in place, and it's your responsibility to create those processes to fit your use case. This is actually really great, and in many use cases is exactly what you want because it gives you a great deal of control over your solutions. Whatever happens on your instances and with your instances is in your hands. You can create simple or complicated setups that run and scale on AWS exactly to your specification. That being said, not every single solution requires this level of control over the underlying environment. Oftentimes, you might be looking to focus on your own business solutions and let someone else take care of the undifferentiated heavy lifting for you. Or perhaps you just simply don't want to fiddle around with scaling controls and fault-tolerant designs, but you still want all of the benefits of doing so. This is where the term serverless comes in. A lot of AWS services are serverless in nature. Serverless means that you cannot see or access the underlying infrastructure or instances that are hosting your solution. Instead, all of the management of the underlying environment from a provisioning, scaling, fault tolerance, and maintenance perspective are taken care of for you. All you need to do is focus on your application. The rest is taken care of, or more accurately, the rest is abstracted from you. This means that serverless offerings are very convenient to use. You get to focus on the value that the service delivers and not the underlying implementation details, thus reducing the number of operational support processes that you need to have in place. Remember the shared responsibility model that we covered in a previous lesson? This idea of serverless impacts that as well. For example, with Amazon EC2 instances, you are required to patch the OS when new security updates are released. With serverless offerings, the line between what you are responsible for versus what AWS is responsible for moves up. You do not have access to the underlying operating system that is running the service. Therefore, you cannot be responsible for carrying out tasks like patching. You are, however, still responsible for things like data encryption and access management. Let's wrap this up. I like to think of AWS services as existing on a spectrum. On one side of the spectrum, you have convenience, and on the other side, you have control. Many services exist to give you control, like Amazon EC2, whereas other services exist to give you convenience, like the serverless compute AWS Lambda. We'll dive deeper into some of these serverless compute technologies coming up. Now that you have learned about what container services AWS offers and what serverless means, let's continue our conversation about containers. To recap, ECS or EKS is the container orchestrator. This is the tool that is managing the container's lifecycle. Then you need the compute platform. This is where the containers actually run. Previously, you learned that ECS and EKS run containers on clusters of EC2 instances. And in that case, you are using EC2 as the compute platform for your containers. And you also have tight control over those instances. Now, EC2 is certainly not serverless, so thinking about serverless compute for containers, I want to introduce to you a service named AWS Fargate. AWS Fargate is a serverless compute platform for containers that you can use with either ECS or EKS. With AWS Fargate as the compute platform, you run your containers on a managed serverless platform. The scaling and fault tolerance is built in, and you don't need to worry about the underlying operating system or environment. Instead, you define your application content, networking, storage, and scaling requirements. There is no provisioning, patching, cluster capacity management, or infrastructure management required. To break that down a bit, the way you work with Fargate is you first build your container images and push them into a repository, like Amazon Elastic Container Registry, for example, which is a place where you can store container images for them to be pulled and deployed from. So you have your container images in your repo, and then you define memory and compute resources for your task if you're using ECS, or your pod if you're using EKS. Then you run your containers. And at the end, you only pay for the amount of vCPU, memory, and storage resources consumed by your containerized applications. Fargate does support spot and compute savings plan pricing options, just like with Amazon EC2 instances. So there is some flexibility on how you plan to run containers on Fargate. So you can still get a good amount of control for your containers deployment, but without needing to worry about the provisioning, patching, and managing the underlying operating systems or instances, and no need to scale the infrastructure in and out to meet demand like you do with EC2. As far as use cases go, AWS Fargate can be used for all of the common container use cases, including microservice architecture applications, batch processing, machine learning applications, and migrating on-premises applications to the cloud. All right, hopefully you now have a 10,000-foot view of AWS Fargate. You can see how Fargate is an example of how serverless simplifies your operations and management for running scaled container solutions. AWS Lambda is one of the serverless compute options you have available to you on AWS. Lambda allows you to package and upload your code to the Lambda service, creating what is called a Lambda function. Once you create a Lambda function, it isn't always running all of the time. Instead, Lambda functions run in response to triggers. You can configure a trigger for when you want your function to run, and from there, the Lambda service waits for the trigger or polls for an event to trigger the function, depending on what the trigger is that you choose. There's a long list of available triggers for AWS Lambda, and new ones are being supported all of the time, so I won't run through them all now. However, a couple of common examples of triggers for Lambda functions are an HTTP request, an upload of a file to the storage service Amazon S3, events originating from other AWS services, or even in-app activity from mobile devices. When the trigger is detected, the code is automatically run in a managed environment, an environment that you do not need to worry too much about because it is automatically scalable, highly available, and all of the maintenance of the environment itself is done by AWS. You do, however, get to choose the language your Lambda function is coded in, the amount of memory and CPU your function is allocated in the environment, permissions, dependencies, and many other aspects of how the function runs. If you have 1 or 1,000 incoming triggers, AWS Lambda will scale your function to meet demand, each in its own isolated environment. Lambda is currently designed to run code that has a runtime of under 15 minutes. So this isn't for long-running processes like deep learning or batch jobs. You wouldn't host something like a WordPress site on AWS Lambda. It's more suited for quick processing like a web backend handling requests or a backend report processing service or microservice hosting. One of the best things about Lambda is that you aren't billed for code that isn't running. You only get billed for the resources that you use, rounded up to the nearest 1 millisecond interval. To understand Lambda more thoroughly, let's run through a quick demo. In this demo, I will create a Lambda function that resizes images uploaded into the employee directory to be uniform thumbnail size. It makes sense to create this sort of logic with the Lambda function. You don't need an application to be running 24/7 on EC2 to resize photos uploaded to the application. You really only need to run the resize logic when a new photo is uploaded. So here's our diagram for the app. What I want to do here is when a new photo is uploaded to S3, it triggers a Lambda function that then resizes the image and uploads it into that same S3 bucket, but to a different location than where the original image is stored. All right, let's go ahead and build this out. You can see that I'm already in the AWS Lambda console, and I'm going to first click Create Function. Next, we get to select what type of function we want to build. Do we want to author a function from scratch? Do we want to use a blueprint, which will give you some sample code and configuration presets? Or you can use a container image with AWS Lambda, as Lambda does support running containers. We're going to author a function from scratch. For the function name, we will call this resize image, and then we get to select the runtime. The runtime is the language that your Lambda function is written in. Because with Lambda, it runs in the Lambda environment, but it's still your code. So I'm going to go ahead and select Python 3.9 for this, as we wrote this function in Python. And then we have to select the permissions. And the permissions are going to be delegated to the function through IAM roles. So I'm going to click Use an existing role. And then if I expand this dropdown, we can select Lambda S3 Full Access, which is an IAM role that I've already created in this account that will give this function permissions to read and write from S3. Now we can scroll down and select Create Function. Now we can add a trigger for this Lambda function, and I'll select Add Trigger. And here we get to configure the trigger source. And if we expand this dropdown, you can see a list of AWS services that can act as triggers, like API Gateway, an Application Load Balancer, DynamoDB. We're going to scroll down and select S3 for our trigger. And then we need to select which S3 bucket will be the event source. I already have an S3 bucket created in this account called Photo Upload Bucket MW. We'll select that one. And then if we scroll down, I'm going to select the event type. I want to select only a put, so I want put operations to trigger this AWS Lambda function. Then we can provide a prefix. With this prefix, what we're essentially doing is we're going to say, I only want to trigger this Lambda function if a put occurs in a specific location inside of this bucket. We're going to upload photos to an input prefix, and that will then trigger the Lambda function. We then need to acknowledge that if we're using the same S3 bucket for both input and output, that it could cause recursive invocations. So the way that we're getting around that is by supplying this input prefix. The event will be triggered when an image is uploaded to this prefix, but then the output will actually be uploaded to a different location. We'll have an output prefix where the image will be uploaded to. So we're going to go ahead and acknowledge by checking this checkbox and then click Add. Now back on our function overview page, what we need to do next is actually upload the code for this. So if we scroll down, we can select the Code tab. And then you can see that there's a stubbed out Lambda function here that essentially just says, hello world, hello from Lambda. And what we need to do is upload our code. So I'm going to click Upload From, and then select Zip File. Click Upload, and then I will select this resize image.zip. Click Open, and then click Save. All right, our function has been successfully created. We have our trigger defined, and we have our code uploaded. What I want to do now is test this out by actually uploading an image to S3 and then viewing the output. So in the search bar, I'll type in S3 and then select S3. Then from here, we'll select the bucket, and then we'll go into the input folder and then select Upload. Click Add Files, and then I'll upload Ceph's image and select Open, and then Upload. We can see that that upload was successful. So now if we go check, we should see the output with the thumbnail version of that image. So now going back into our bucket, if we go up one level, we can now see that the output prefix has been created, so I'll select that. And we can see that the thumbnail image was created.
And that's it. That's how you create an AWS Lambda function. You could host the entire employee directory application's backend on Lambda with some refactoring, but I'm going to go ahead and save that for a later conversation. At this point, you've covered a few different AWS compute services. The services covered so far can handle a wide variety of use cases. So how do you know when to use each one? To figure that out, I think it's time to play a game. Welcome to the Which AWS Compute Service Should I Choose for My Use Case game show. We're your hosts, and you're the contestant.
We will present 3 different use cases that require compute on AWS, and it's up to you to choose the right service for the use case. You'll have 5 seconds to answer each question. Ready?
I'm ready, and I hope you are too. Let's do it. First question is up. Consider a scenario where you are a developer who is tasked with creating a new feature for a web application being hosted on EC2. The web application is an online store, and right now all the items being sold in the store are loaded into a database manually behind the scenes. By manually, I mean there is a person who adds a new row to a database for each new item to be sold in the store. This process takes a long time, isn't very scalable, and is prone to error. You are tasked with automating the process of getting the new item information loaded into the inventory database. The goal is to have a person upload an inventory spreadsheet into Amazon S3, the object storage service, then have a process automatically load the data into the inventory database.
What compute would you use to host the processing logic to load the items from the file into the database? 5 seconds on the clock.
All right, let's discuss how you could have answered this question. You could have decided to use Amazon EC2 here. You could spin up a new instance specifically for this process and write some code that pulls the location of the spreadsheet for a new upload every so often, updating the database when it finds a new file. That would work, but before I make my final answer here, I have a question. How often does new inventory get added to the database?
New inventory gets updated once a quarter.
Good to know. So it's not very often, which means this process would only run once a quarter, and that does change my answer. Here's why. Amazon EC2 charges per second or per hour, so if I have an instance running all the time to serve requests that happens once per quarter, that seems like a lost opportunity to optimize for cost. I would be spending money on a resource I rarely use. It certainly would work, but it may not be the best fit for this use case. I could automate the process of starting and stopping the instance when needed, but instead, what about using AWS Lambda?
Bingo! AWS Lambda is the correct answer for this one. There are a few reasons. First of all, to address your concern on cost, AWS Lambda only charges you for the compute you consume when the code is actually running, and code is only run in response to triggers or a direct invocation. So here's my suggestion. You know that the goal is to have someone upload an inventory document to S3, which should kick off the process of updating the database. You also learned that AWS Lambda has triggers that run your Lambda functions code. AWS Lambda integrates with many AWS services to act as triggers, and Amazon S3 is one of them. So, my suggestion would be to create an AWS Lambda function, configure a put event as the trigger from Amazon S3, then when the inventory is uploaded, Amazon S3 will trigger the Lambda function to run, and the code in the function will parse the inventory document and add each item to the database.
Okay, great. Time for the next question. Let's say you have an application currently hosted in your on-premises data center, which needs to be migrated to AWS. It's currently running on Linux servers in the data center, and you want to minimize the amount of refactoring needed to migrate to AWS. It's important that this workload is elastic and can support varying demand. What compute option would you choose? 5 seconds on the clock.
Time's up. Now I'll go over the answer. Considering the fact that minimizing refactoring is an important aspect of this workload, I would architect a solution using Amazon EC2 as the compute service. EC2 instances can be launched from Linux-based AMIs, and the application could be hosted on the EC2 instance the same way it would be hosted on a Linux server on premises. Amazon EC2 also has the ability to scale in or out based on demand, so I think EC2 is the best service for this one.
That's correct. So if you answered EC2 at home, good work. Before we move on to the final question, let's dive into this answer a little more. Morgan, can you explain the thought process behind eliminating the other compute services we covered in the answers to this question?
Sure thing. So, AWS Lambda could work, but you can't just upload the same code you would run on Amazon EC2 into a Lambda function. There would have to be a decent amount of refactoring in order to take advantage of that service. Same idea with any of the AWS container services like ECS or EKS. Again, you'd have some amount of rework required to migrate to containers. Therefore, Amazon EC2 is the best option for this migration. Now, time for one final use case, and this one is for all the marbles. Imagine a scenario where you are planning to write a brand new application using a microservices or service-oriented design, and you want to architect the application where it can scale up or down quickly, and you want to lower the risk of deploying new changes to production. Which AWS compute service would you use? 5 seconds.
Okay, time's up. The answer for this use case is one of the AWS container services like Amazon ECS or Amazon EKS.
Correct.
The answer is either ECS or EKS for this one, because using containers makes it easier to support microservice or service-oriented designs. Containers boot up quickly, so scaling is quicker than EC2 instances, and the use of containers helps with code portability. Meaning, if I write the code on my laptop and run it in a container, test it in QA in a container, I can then expect the same container to behave the same way once deployed to production, thus reducing the risk of deployments causing errors because of environmental issues.
All right, there you have it. Different use cases for a few of the AWS compute services. Make sure you read up on AWS's other compute offerings and make informed decisions when architecting your solutions. You'll find there are a lot of options.
Remembering that these services exist to best suit different use cases helps. Don't try to use the same compute service for all of your use cases. Instead, pick the right one for the job and consider re-evaluating choices for existing workloads as AWS continues to release and improve offerings. Hello again. I'm so happy to see that you've made it to this next batch of lessons in our course. So far, you've learned about compute and networking on AWS. Time to move on to two other major categories, storage and databases. The employee directory application we are building out currently has a solid network in place using Amazon VPC and is being hosted on Amazon EC2. The only issue is the app doesn't really work yet because we haven't set up anywhere for it to store the employee information or the employee photos. We are going to go ahead and fix that. We will start off by learning about the different storage offerings AWS has and compare and contrast them. Then we will create an Amazon S3 bucket in our account that the employee directory app will use to store employee images. Then we will explore the different database services AWS has, and there are a lot. Not to worry though, we are focusing on two, Amazon Relational Database Service, or RDS, and Amazon DynamoDB. As always, take the quizzes and please take a good look at the readings that we have placed between the video lessons. There's a lot of extra information there that could be useful to you as you continue your journey with AWS. Great work so far, keep it up, and we'll see you in a bit.
The next thing we need to configure for our employee directory app is the storage. Our application requires several types of storage for its data. For one, we need to store the operating system, software, and system files of our app. We also need to store static assets like photos for the employee headshots, and then we have more structured data such as the name, title, and location of each employee as well. All of that needs a home. The structured data usually requires a database, which we'll talk about later this week. So for now, we'll focus on storing the application files as well as the static content. There are two main types of storage that we can use to store this data, block and object. Here's the difference. Let's say that I have a 1 GB file with text in it. If I'm storing this in block storage, what happens is that this file is split into fixed size chunks of data and then stored. Object storage, on the other hand, treats each file like a single unit of data. This might seem like a small difference, but it can change how you access and work with your data. Let's say I want to change one character out of that 1 GB file. If my file is stored in block storage, changing that one character is simple, mainly because we can change the block, or the piece of the file that the character is in, and leave the rest of the file alone. In object storage, if I want to change that one character, I instead have to update the entire file. Let's take these two types of storage and access patterns and try to apply them to the data we want to store. For example, our static data, like the employee photos, will most likely be accessed often, but modified rarely. Therefore, storing in object storage is fine. For more frequently updated data, or data that has high transaction rates, like our application or system files, block storage will perform better. In this section of the course, we'll discuss both block and object AWS storage services and how they'll interact with our employee directory application. Before we do that, take a look at the notes to get a refresher of the different types of storage. That way you can easily match the storage type to the AWS storage service that we talk about. When you launch an EC2 instance, you're going to need some kind of block storage to go with it. This block storage can be used as a boot volume for your operating system, or a separate data volume. For example, think about your laptop. With a laptop, you store your data in drives, and those drives are either built in internally to your laptop or connected externally. EC2 instances have the same options as far as block storage goes. The internal storage is called Instance Store, and the external connected storage is called Amazon Elastic Block Store, or Amazon EBS. Let's talk about Instance Store first. Instance Store is a form of directly attached storage, which means the underlying physical server has at least one storage unit directly attached to it. This direct attachment is also the main advantage of using this form of storage. Because it's so close to the physical server, it can be very fast and respond very quickly. But while it can be very fast, there is also one big downside. With Instance Store being directly attached to an EC2 instance, its lifecycle is tied to that of the instance. That means if you stop or terminate an instance, all data in the Instance Store is gone. It can no longer be used or accessed. Naturally, there are many use cases where you want the ability to keep data even if you shut an EC2 instance down. This is where EBS volumes come in. These volumes, as the name implies, are drives of a user-configured size that are separate from an EC2 instance. The drives are simply network-attached storage for your instances. You can think of it as similar to how you might attach an external drive to your laptop. You can attach multiple EBS volumes to one EC2 instance, and then you can configure how to use that storage on the OS of the EC2 instance. When I connect that EBS volume to my instance now has a direct communication line to the data in that volume. Nobody else can directly talk to that volume so that it maintains secure communication. You need an EC2 instance to access data on an EBS volume. If I decided I want to use that EBS volume with a different instance, that's no problem. We can stop the instance, detach the volume, and then attach it to another instance in the same AZ, much like you can unplug your drive from a laptop and plug it into another one. Or, depending on the instance type and EBS volume we're using, we may be able to attach it to multiple instances at the same time, which is called EBS multi-attach. And perhaps the most important similarity is that an EBS volume is separate from your instance, just like an external drive is separate from your laptop. That means if an accident happens and the instance goes down, you still have your data on your EBS volume. This is what we refer to as persistent storage. You can stop or terminate your instance, and your EBS volume can still exist with your data on it. EBS is often the right storage type for workloads that require persistence of data. However, the question typically comes down to which EBS volume type do I use? That's right, there are many different types of volumes, but they've divided into two main volume types: SSD-backed volumes and HDD-backed volumes. In the readings, you'll learn more about these two options. The last thing we'll need to talk about here is backing up data. Things fail, errors happen, so you need to back up your data, even in AWS. The way you back up EBS volumes is by taking what we call snapshots. EBS snapshots are incremental backups that are stored redundantly. The idea here is that if something goes wrong, you can create new volumes from your snapshots and restore your data to a safe state. So we've figured out block storage for our application. Now we need to figure out where to store our employee photos. A natural question is, why can't we just store these photos in Amazon EBS? Well, there's a few reasons. Number one, most EBS volumes are only connected to one EC2 instance at a time. Multi-attach is not supported by all volume and instance types. Eventually, as my app scales, I'll need to figure out how to access those photos from all of my instances. That's an issue. The second consideration is that an EBS volume has size limitations. That means that eventually there will be a limit to how many HD 4K photos I store of my employees in one drive. Ideally, I'd store these photos in a more scalable solution. So, EBS probably isn't the right choice. Fortunately, AWS has a service called Amazon Simple Storage Service, or Amazon S3, that was designed to be a standalone storage solution that isn't tied to compute, meaning you don't mount this type of storage onto your EC2 instances. Instead, you can access your data through URLs from anywhere on the web, which gives this service its nickname, Storage for the Internet. S3 also allows you to store as many objects as you'd like with an individual object size limit of 5 terabytes. This makes it ideal for our employee photos. Now, let's talk about how we store things in S3. The underlying storage type for S3 is object storage. That means that all of the same characteristics of object storage are also characteristics of S3. So S3 uses a flat structure, it uses unique identifiers to look up objects when requested. You get the idea. S3 is also considered distributed storage, meaning that we store your data across multiple different facilities within one AWS region. This is what makes S3 designed for 99.99% availability and gives it 11 nines of durability. All right, let's learn about some S3 concepts. The first concept is a bucket. In S3, you store your objects in a bucket. You can't upload any object, not even a single photo, to S3 without creating a bucket first. You then place your objects inside of these buckets. And if you want to organize and arrange those objects, you can also have folders inside of the buckets. Let's create a bucket in the console. When you log in, you'll type S3 in the service search bar. Once you click on it, you'll see the S3 dashboard showing you all the available buckets for every region. I'll then select Create Bucket. What I want to point out here is that buckets are region-specific, so we can choose where we want to place our bucket. In this case, we want to place our bucket close to our infrastructure for our application, which is in the Oregon region, so we'll choose Oregon. Next, we have the name of our bucket. Even though our bucket is specific to one region, our bucket name has to be globally unique across all AWS accounts and must be DNS compliant. Once you create your bucket, AWS will construct a URL using this name, so it has to be something that is reachable over HTTP or HTTPS, meaning there can be no special characters, no spaces, etc. So, for this bucket's name, let's choose employee-photo-bucket-sr-001, which is DNS compliant. Now we can leave the rest as defaults. Scroll down and click Create. To work with this bucket, I'll need to find it in the list and click on its name. Here, we can start uploading our objects. To do this, I'll click Upload and then Add Files. Now I can choose any file I want and then I'll click Upload. So, as you can see, the object upload was successful. If I click on the name of my object, I'll be able to see quite a bit of detail. I can see the owner, region, and size. But most importantly, we can see the URL of my object. The first part of this URL is simply my bucket URL that AWS created using the bucket name. Then AWS appended the name of my object, also referred to as the object key, to the bucket URL. Now, what happens if I click on this URL? Access denied. That's weird, right? Well, not really. That access denied message leads us to a bigger question that most people have when they start out on AWS, and that's, who can access my data? Earlier I mentioned that you can retrieve your data from anywhere on the web. And people often think that means that anyone can retrieve that data. By default, it's actually the opposite. Everything in S3 is private by default. This means that all S3 resources, such as buckets, folders, and objects, can only be viewed by the user or AWS account that created that resource. That's why I got an access denied message, because I was acting as an anonymous user on the internet trying to access an S3 object that's private. Now, that's not to say no object or bucket can be open to the world. They absolutely can be if you explicitly choose that option. And it's actually kind of a process to make something public. The reason it's difficult to make your objects public is to prevent accidental exposure of your data. Let's try it. Okay, so if we want to make the object we created public, we need to do a few things. Normally, from the Object Detail page, we would be able to click on the Object Actions dropdown and then select Make Public using ACL. But it is currently not available for us to select. Going to the Bucket Details page, I can select the Permissions tab and see that there is a default setting that blocks all public access. From there, I can verify that Block Public Access bucket setting is set to block all public access. I'll click Edit, then uncheck the top box that blocks all public access, and then save the changes. I'll type Confirm to make the change, and then click Confirm to finalize it. From there, I'll go back to the Bucket Permissions tab and scroll down to the Object Ownership section and click Edit for this pane. Instead of the default setting to disable access control lists or ACLs, I'll select ACLs enabled, then acknowledge, and then save the changes. Now I can go back to the Object Details page and select Make Public using ACL from the Object Actions dropdown. This will allow me to make the object public. To view the object, all I need to do is go back to the Object Details, find the URL, and click on it to view the photo. That's how you make an object public. That being said, most of the time you don't want your permissions to be all or nothing to where either nobody can see it or everybody can see it. Typically, you want to be more granular about the way you provide access to resources. As far as access control, you can use IAM policies attached to users, groups, and roles to access your S3 content, and you can also use a feature called S3 bucket policies. S3 bucket policies are similar to IAM policies in that they are both defined using the same policy language in a JSON format. The difference is IAM policies are attached to users, groups, and roles, whereas S3 bucket policies are only attached to buckets. S3 bucket policies specify what actions you're allowed or denied on the bucket. For example, you might want to attach an S3 bucket policy to it that allows another AWS account to put objects in that bucket. Or you might want to create a bucket policy that allows read-only permissions to anonymous viewers. S3 bucket policies can be placed on buckets and cannot be used for folders or objects. However, the policy that is placed on the bucket can apply to every object in that bucket. All right, to recap, S3 uses containers called buckets to store your objects, and you have several options to control access to those objects through the use of IAM policies and bucket policies. Thank you, and welcome back to everyone's favorite game show, which AWS storage service do I use for my use case? Today we have one contestant during the final round of our show, and that's you.
In order to win the grand prize, you must answer the next 3 questions correctly. There will also be a bonus question, so there's an opportunity to get extra points. All right, once we read the question, you have 5 seconds to answer to get points. Let's get started.
All right, this is the first question. Let's say you're a developer and you plan to build out an application to transcode large media files like videos. You'll be using an AWS Lambda function to perform the transcoding, but you need a place to store both the original media files and the transcoded media files. Due to regulations, you need to store these files for at least a year. Which of the storage services that we've talked about in this course should you use? You have 5 seconds to answer. And the answer is Amazon S3. Why is S3 the best solution here, Morgan?
Well, first of all, the question says that they're using a Lambda function. Because of that, I'm already ruling EBS out, as EBS volumes can only be attached to EC2 instances.
Even if they were using EC2, video files are typically large in size, so you may have to use multiple EBS volumes to store that data, which might not be cost-effective in the long run. So EBS is out. Instant storage is out for the same reason. We're not using EC2 here, but also because we want this data to persist for a year, and instant storage is considered ephemeral.
All right, S3 it is. Let's put some points on the board for those who got it right. Morgan, tell us the next question.
The next question is, you're an architect for an e-commerce company that wants to run their MySQL database on an EC2 instance. This database needs a storage layer to store their order and customer information. The database will frequently be accessed and updated, so the storage layer needs to respond quickly. It's important that the storage is fast and durable. Which AWS storage service should you use? You have 5 seconds. And the answer is Amazon EBS. Add 30 points to your score if you got it.
It seems like we're looking for storage attached to the compute, so why not EC2 Instant Store?
Right, that's also an option, but it's not ideal. Since it's an e-commerce company, their order and customer data is what drives the business, which means the persistence and durability of that data is really important. Using EC2 Instant Store would definitely give us the speed we're looking for, but it wouldn't give us the durability needed to store this data long-term. So EBS is the right option.
That makes sense. All right, moving on. 2 more questions. The next one is, you have a web application that needs to write to disk in order to perform certain calculations. The application will store temporary data during the calculation. The most important aspects of this architecture are speed and cost. With 5 seconds on the clock, which storage solution would you choose? And the answer is EC2 Instant Store.
Seth, would you mind telling us how we chose Instant Store and not EBS?
Sure. Once again, we're looking for storage attached to compute in this case. The first thing I want to point out is that this is temporary data we're talking about. We're not looking at a huge amount of data, and we also don't necessarily care about the durability of that data. If the instance fails mid-calculation and you want to plan for failure, you can just restart the calculation from scratch. So durability doesn't matter, but cost does. By not using EBS and instead using Instant Store, you may save yourself some costs. That is because Instant Store is included in the overall EC2 instance price, so Instant Store is the best option for this use case.
Okay, 30 more points on the board for those of you who got it. Now, the final bonus question for an extra 10 points is next. This is a tricky one, and you might have to think outside of the storage options that we've talked about so far. The question is, let's say you're creating a WordPress site on multiple instances. By default, WordPress stores user uploads on the local file system. Since you want to use multiple instances, you'll need to move the WordPress installation and all of the user customizations into a shared storage platform. Which storage option would you use? 5 seconds to go. And the answer is Amazon Elastic File System, or Amazon EFS. This service was covered in an earlier reading, so if you got points for this, great job. For those of you who didn't, no worries, but I would recommend that you go back and review the reading related to file storage on AWS.
Let's go ahead and talk about the options. Typically, when we talk about shared storage systems that multiple instances can access, we think Amazon S3. Why wouldn't we use that in this case?
Well, S3 isn't a file system. It's actually a flat structure for storing objects instead of a hierarchy, and you can't mount it onto multiple instances. Because S3 has a different underlying type of storage, it's not right for this use case. So by moving the entire WordPress installation directory onto an EFS file system and mounting it onto each of your EC2 instances when they boot, your WordPress site and all of its data is automatically stored on a distributed file system that isn't dependent on any one EC2 instance.
Nice. Well, you answered all 4 questions and you win the grand prize of the satisfaction of getting them all right. Congratulations, and that's it for today's show.
Hey everyone, welcome to our exercise walkthrough on creating an S3 bucket and then modifying the EC2 instance holding the application to utilize this S3 bucket. As you can see, I'm already in the AWS Management Console and I'm logged in as the admin user that was created before. So the first thing that I need to do is to create the S3 bucket that will be utilized by the application. To do that, I'm going to go up to this search bar here and type in S3 and then click on the S3 service to be taken to the S3 console. Now that I'm in the S3 console, I'm going to go ahead and click Create Bucket. And for my bucket name, I am going to use employee photo bucket dash SR as my initials, and then dash and just 3 random digits. So I'm going to go with 963. I do want to make sure that my bucket is in the same region as the rest of my infrastructure. So I'm going to keep this as the Oregon region or US West 2. And then I'm going to keep all of the other defaults as they are. From there, I'll go ahead and click Create Bucket. And as you can see, my bucket has been successfully created. Now that the bucket has been successfully created, I want to test uploading an object just to make sure that it all works. So I'll click on the name of the bucket, which will take me to the bucket details page. And to upload a file, I can click this upload that's in the center of the page here, but more often I'm going to use the one in the upper right. So I'll click that upload button and then I'll click add files, and I'll go ahead and upload this employee to photo. After I add that file, I can click upload, and as you can see, the upload of that file was successful. So I'll go ahead and click close there. And in a previous demo, you might have seen a way to make this object publicly accessible. But for this bucket and for the exercises moving on, we don't want this bucket to be just completely open to the world. We want this bucket and these objects to specifically be accessed by the application. And so in order to do that, we need to adjust the permissions for this bucket, specifically the bucket policy. So since I'm already in the bucket details page, I'm going to go ahead and click on this permissions tab, and I want to adjust the bucket policy for this bucket. So I'm going to scroll down to bucket policy and click the edit button, which will take me to a spot where I can create a bucket policy. So to create this bucket policy, I'm going to take the policy that is in the exercise instructions and paste it here. But before I move forward, before I save this policy, I need to edit a few things. The first thing that I need to edit is the account number so that I am utilizing the correct account. And that will be done here where it says insert account number. And I will paste my account number there. And then from there, I will also scroll down and change this area where it says insert bucket name and put my bucket name there. And I need to make sure to do that in both locations, and make sure that I'm also removing the caret brackets when I do so. So now that I've done that, I can go ahead and save these changes, and my bucket policy will be created. And now my account with this specific role will have access to this bucket and the objects within this bucket. So now that I have tested uploading an object and created the bucket, as well as providing access to the bucket by that role, I need to modify the application to utilize this bucket. So to do that, I'm going to go over to EC2 and click on Instances. And as you can see, my stopped instance from previous exercise is there. And there's a cool little shortcut that can be used in order to clone this instance so that I'm launching basically the exact same thing and making sure that I maintain those settings. So to do that, what I'll do is I'll select this stopped instance, and then I'll go over to Actions and down to Image and Templates, and then I can click Launch More like this. What that's going to do is open up my instance launching page, but already have certain things filled out so that my instance is going to be a clone of the stopped instance that I've already launched. So what I want to do is make sure that I know that this is my updated application instance. So to do that, I'm going to append -S3 to the end of the instance name. So it'll be employee directory app S3. And my image and instance type are going to remain the same. So what I can do is just make sure that I'm using the same key pair that I'm using with my other instances. And then I want to scroll down and make sure that this is going to be accessible. So I want to change my auto assign public IP to enable. And that's just going to make sure that I have a public IP address to access for this instance. From there, I'm going to continue to scroll down as all of the other settings are still correct. And then I'm going to expand advanced details. With the expanded advanced details, I can see that the role is already associated to this instance. And I'm going to scroll all the way down to the user data. And what I need to do is put my bucket name in here so that now my application knows what bucket to utilize. And so with my bucket name there, I can now launch my instance. And that will just take a little bit of time. So I'll go over to my instances and I'll wait for that to be launched, just occasionally refreshing it to make sure that everything launches correctly. And I want to wait until the status check is showing 2 of 2 checks passed. So now that I've given it some time, I'm going to go ahead and click refresh again. And as we can see, there are 2 of 2 checks passed. So I just want to make sure that this application is up and running. I will select this instance and copy its public IP address. And then in a new tab, I will go ahead and paste that IP address. And as we can see, the application is up and running. We still can't interact with this application yet because the database hasn't been associated. So that is just to make sure that the application is up and running, and we'll be able to interact with it in just a bit. So now that that's been done, just want to do a couple of the closeout tasks for this. And so just make sure that you, if you're following along or if you've already done this, that you go ahead and stop this instance as well as delete the object that was uploaded to the S3 bucket. And that'll just make sure that you don't accidentally accrue any charges outside of running this exercise. All right, that's it for this one, and I will see you in the next exercise.
The employee directory application that we've been building out lets you keep track of employee data like their name, location, job title, and badges. The app supports adding new employees, viewing existing employees, as well as editing and deleting employees. All of this data will be stored in a database, which we haven't created yet. According to the architecture diagram, we have chosen Amazon Relational Database, or Amazon RDS, to store this data. So let's talk about databases for a moment.
relational databases are widely used across all industries, and it's likely your company has many databases supporting a variety of applications and solutions. Relational Database Management Systems, or RDBMS, let you create, manage, and use a relational database. You can install and operate database applications on Amazon EC2 instances, and this is a good option for migrating existing databases to AWS. By running databases on EC2, you are already simplifying things from an operational perspective when it comes to on-premises, and it's a common use case for EC2. When migrating a database from on-premises to EC2, you are no longer responsible for the physical infrastructure or OS installation, but you are still responsible for the installation of the database engine, setting up across multiple AZs with data replication in place, as well as taking on any database server management tasks like installing security patches and updating database software when necessary. So EC2 makes it easier, but there is a way to lift even more of the operational burden of running relational databases on AWS. What if instead of managing a database on EC2, you could use one of the managed AWS database offerings like Amazon RDS? The big difference between these two options is instead of taking care of the instances, the patching, the upgrades, and the install of the database, AWS takes care of all of that undifferentiated heavy lifting for you. The task that you are then responsible for is the creation, maintenance, and optimization of the database itself. So you are still in charge of creating the right schema, indexing the data, creating stored procedures, enabling encryption, managing access control, and more. But all of the rest of the undifferentiated heavy lifting that goes into operating a relational database, AWS takes care of. To start off this section of lessons on databases, we will first cover RDS. The upcoming reading after the video will dive into the history of enterprise relational databases and explain what relational databases are and how they were used. If you aren't familiar with databases, the readings coming up will give you some useful background information. Amazon RDS is a service that makes it easier for you to set up, operate, and scale a relational database. Instead of telling you about RDS, I am going to show you. As you can see, I'm already in the Amazon RDS dashboard. We are going to create the relational database our employee directory application can use to store employee data. First, we will click Create Database, and then we are going to select the Easy Create option, which gives us the ability to accept the standard best practices for backups and high availability. You could select Standard Create if you wanted more granular control to pick and choose the different features of your database setup. Next, you choose the database engine. You can see what is currently supported at the time of this filming for database engines on RDS. And the common engines out there are MySQL, PostgreSQL, MariaDB, Microsoft SQL Server, and then there's this one, Amazon Aurora. Amazon Aurora is an AWS-specific database that was built to take advantage of the scalability and durability of the AWS cloud. Aurora is designed to be drop-in compatible with MySQL or PostgreSQL. It can be up to 5 times faster than the standard MySQL databases and 3 times faster than standard PostgreSQL databases. So if you have some use cases that require large amounts of data to be stored with high availability, durability, and low latency for data retrieval time, consider using Amazon Aurora over a standard MySQL or PostgreSQL RDS instance. In our case, we really only need a simple database without any high performance or large storage requirements. So I'm going to select a standard MySQL instance. Next up, we will choose the database instance size and type. This database instance is similar to how we choose an EC2 instance size and type. Since this is just a demo, I'm going to select a free tier eligible instance. Now we'll give this database a name and assign the database an admin user and password that would be used to connect to the database. Then we will accept the rest of the Easy Create defaults and we are done with this instance creation. You can see that the instance is in the process of booting up, and that will take a few minutes to complete, so in the meantime, let's talk about high availability and RDS. When you create an RDS DB instance, it gets placed inside of a subnet inside of a VPC very similar to an EC2 instance. As you learned already in a previous lesson, subnets are bound to one AZ. And as a best practice for production workloads, we recommend that you always replicate your solutions across at least 2 AZs for high availability. With RDS, one DB instance belongs to one subnet inside of one AZ. So that isn't meeting the criteria for best practices.
Now, before you get worried about managing this all on your own, just know that you can easily configure RDS to launch a secondary DB instance in another subnet and another AZ using RDS multi-AZ deployment. And RDS will manage all of the data replication between the two instances so that they stay in sync. The other cool thing about RDS multi-AZ deployments is that RDS also manages the failover for the instances. One instance is the primary, and the other is the secondary database. Your app connects to one endpoint. If the primary instance goes down, the secondary instance gets promoted. The endpoint doesn't change, so no code change is needed. All of the failover happens behind the scenes and is handled by RDS. All you do need to do is to make sure that your app can reconnect to the database if it experiences a momentary outage by updating any cached DNS lookups and reconnecting to the endpoint, which now connects to the secondary instance. Pretty cool if you ask me. All right, and we're back in the console and we can see that our instance is up and running. At this point, you can connect to the database instance and load your database schema onto it, ready to go, and much, much simpler than trying to install and manage this all on your own. Using services like RDS make operating databases significantly more accessible and lowers the operational overhead that comes along with relational database management. Before we move on to learning about Amazon DynamoDB, I want to touch on an idea that's important when you're making architecture decisions for your AWS solutions. Choosing the right database to fit your business requirements rather than forcing your data to fit a certain database choice. There is no one-size-fits-all database for all purposes. You should pick a database that fits your specific use case. And with AWS, you have multiple choices for databases. We covered Amazon RDS and relational databases, and that was the default option for businesses for a long time. But relational databases aren't the best choice for all business needs. AWS creates services to support purpose-built databases, meaning that there are many database services that AWS offers, and they each were built with a certain use case in mind and therefore are optimized for those use cases. Let's think about the employee directory app. We had originally decided that we would use RDS for the database, but now, after thinking about it some more, RDS might not be the best fit for our needs. All we are really doing is storing one record in a table for each employee. There are no complex relationships that need to be managed, and it's essentially just a lookup table. Relational databases offer all sorts of features that are great for complex schemas and relationships, but those features add overhead that is unnecessarily complex for simple things like a lookup table. On top of that, the RDS option we chose charges per hour of instance runtime, so we will get charged for the running instances regardless of whether we're using it or not. Our employee directory application will have much higher usage during the week and no usage on the weekends. Is there an AWS database offering that better fits our needs? Introducing Amazon DynamoDB. Amazon DynamoDB is a NoSQL database that is great for storing key value pairs or document data. This service works great at a massive scale and provides millisecond latency. It also charges based on the usage of the table and the amount of data that you are reading from the table, not by the hour or by the second. This is a better option for our simple employee lookup table. Now, besides the employee directory app, there are other use cases that require databases of varying types. What if you are writing an application that needs a full content management system? Neither RDS nor DynamoDB would be the best solution. Luckily, AWS has quite a number of other database offerings. For this use case, you might look into Amazon DocumentDB. It's great for content management, catalogs, or user profiles. Let's think of another use case. What if you had a social network that you wanted to track? Keeping track of those kind of social webs, figuring out who is connected to who, can be difficult to manage in a traditional relational database. So you could use Amazon Neptune, a graph database engineered for social networking and recommendation engines, but is also good for use cases like fraud detection. Or perhaps you have a supply chain that you have to track with assurances that nothing is lost, or you have a banking system or financial records that require 100% immutability. What you really need is an immutable ledger. So perhaps Amazon QLDB or Quantum Ledger Database is a better fit for this use case. It's an immutable system of record where any entry can never be removed and therefore is great for industries that need to be audited for regulatory and compliance reasons. It can take a lot of experience and expertise to operate databases at scale, and that's why it's so beneficial to utilize one of the AWS database offerings. You don't need to be an expert on running all of these different types of databases. Instead, you can just use the database service that is best for your use case and focus on your application and providing value to your end users. You don't need to build up a ton of in-house expertise to operate a highly scalable, immutable ledger database. You can just use AWS QLDB instead. The key thing to understand is AWS wants to make sure that you are using the best tool for the job. Coming up next, we will explore Amazon DynamoDB and get a look at more of the details. Let's talk some more about Amazon DynamoDB. At the most basic level, DynamoDB is a database. It's a serverless database, meaning that you don't need to manage the underlying instances or infrastructure powering it. With DynamoDB, you don't create a database with tables that relate to each other like a relational database. Instead, you create standalone tables. A DynamoDB table is just a place where you can store and query your data. Data is organized into items, and items have attributes. If you have one item in your table or 2 million items in your table, DynamoDB manages the underlying storage for you, and you don't need to worry about scaling the system up or down for storage. DynamoDB stores data redundantly across AZs and mirrors the data across multiple drives for you under the hood. This lessens the burden of operating a highly available database. DynamoDB, beyond being massively scalable, is also highly performant. DynamoDB has a millisecond response time, and when you have applications with potentially millions of users, having scalability and reliable lightning-fast response times is important. Now, DynamoDB isn't a normal database in the sense that DynamoDB doesn't require a rigid schema or manage complex relationships or constraints. Relational databases, like the MySQL database we created in an earlier lesson, require that you have a well-defined schema in place that might consist of one or many tables that may or may not relate to each other. Relational databases work great for a lot of use cases and have been the standard type of database historically. However, these types of rigid SQL databases can have performance and scaling issues when under stress. The rigid schema also makes it so that you cannot have variation in the types of data that you store in a single table. So it might not be the best fit for a data set that is a little bit less rigid and is being accessed at a high rate. This is where NoSQL databases like DynamoDB are handy. NoSQL databases have flexible schemas. With DynamoDB, you can add or remove attributes from items in the table at any time. Not every item in the table has to have the same attributes. This is great for datasets that do have some variation from item to item. The types of queries you can run on NoSQL databases tend to be simpler and focus on a collection of items from one table, not queries that span multiple tables. This, along with other factors, including the way the underlying system is designed, allow DynamoDB to be very quick in response time and highly scalable. So, things to remember. DynamoDB is NoSQL. It is purpose-built, meaning it has specific use cases and isn't the best fit for every workload out there. Taking a look at our architecture, we modified it to use DynamoDB. We're going to need to create an employee table for the app to write and read from. We will create this DynamoDB table using the console. And you know what? Let's get Seth out here to help us out.
Hello!
We changed our minds about using RDS and decided to change it over to DynamoDB. It's only one table, and it's essentially a lookup table for our employees. How hard do you think this change is going to be to make?
Well, our app is actually designed to use either RDS or DynamoDB as the backend database, so this won't take long at all. Here, I'll show you how. I'm in the console and will navigate to the DynamoDB service. From here, all you need to do is create a new table. Tables in DynamoDB require you to designate certain attributes as keys that will make an item unique. We will select employee ID as the unique identifier for the items in this table. Then we will just accept the defaults and create the table. Our app was coded to look for a table specifically called employees. So this actually should all work now that the table is created. To test it out, let's head over to the website hosted on EC2 and try to add a new employee. See, that was nice and easy. Now let's go back into DynamoDB and refresh the page and scan all the items in the table, and boom, there it is. It's really that simple for a lookup table like this one.
All right, Well, that was easy. Nice. Now, not every use case is this simple. In the reading after this video, there will be more information about how DynamoDB works, so make sure to check that out. Up until this point, you've practiced how to launch an EC2 instance, but you couldn't use the application yet because the storage and database pieces weren't set up yet. In this next lab, you'll add the storage and database components and test that the application is working. To do that, you will create an Amazon S3 bucket and create a bucket policy that will allow the IAM role to work with the objects in the bucket. Then you will upload an object to the bucket manually to get familiar with S3. After that, you will create an Amazon DynamoDB table, which will be used to store employee information. Once the bucket and table are created, you will test that the application can read and write data. That is it for this lab. As usual, if you get stuck, try going back a few steps in the instructions and make sure that you didn't miss anything.
Welcome to our exercise on setting up the database for our application. So we've already created and modified the application and have created and tested the uploading to the S3 bucket. So to get the application fully functional or at a fully functional stage, the next thing to do is to launch a database. But before I launch the database, I want to launch an instance that's ready to use that database so that we can test it as soon as it's done. So to launch that instance, I'm going to go over to EC2 and go over to the instances. And just like with the last time, I'm going to use the shortcut where I launch a clone of an instance that I've already launched. So to do that, I'm going to select my employee directory app-s3 because that's the most updated version of this application. And then I'm going to go over to Actions, Image and Templates, and then I'm going to launch more like this. Now that I'm in that launch page, what I want to do, just so that I know that I am on the correct instance and that I'm using the correct instance, instead of appending -s3 to this, I'm going to append -dynamodb so that I know that this is the application instance that is testing with the database and not just connecting to the bucket. So now that I've adjusted that, I can scroll down. I see that most of my settings are still there. I want to make sure that I'm still using the same key in case I do need to access the instance. And I also want to just verify, even though I know that this works, I just want to verify that I am still using the role. One other thing that I want to make sure to do is to ensure that the instance launches with a public IP, and I scrolled just right over this. And so scrolling back, I go to the network settings and auto assign public IP, and just make sure that I click enable on that. And that way the instance will have a public IP and I can access it and test it once the instance and the database are all fully launched. So now that I've done that, I can see that my user data is exactly where I left it after adding the bucket. And now I can click Launch Instance. As always, give that some time to launch. And I can just go over to the instances and occasionally refresh this in order to make sure that my instance has launched. So I'm going to give this a few minutes while waiting for the instance to launch and making sure that where it currently says initializing, it will say 2 of 2 checks passed. Now that it's been a few minutes, I'll go ahead and refresh the page again. And I can see that 2 of 2 checks have passed. So I'll go ahead and select my DynamoDB labeled instance and copy its public IP address, just because I want to make sure that the application is up and running before I proceed. If this weren't running, as we can see it is, if it wasn't, then I would go back and see where I made a mistake in launching the instance. And once the application was successfully running, then I would move forward with creating the database. And so since I can see that the base employee directory application is up and running, I can go ahead and proceed with creating the DynamoDB table. In order to do that, I'm going to go up to the search bar and type in Dynamo and click on the DynamoDB service. And once I'm here, I'm just going to go ahead and click Create Table. Since I don't have any tables currently running, it's just the easiest way to get to this table creation screen. For the table name, I'm going to put employees because the application is set up to work with a database named employees. So this will make it very easy for it to just utilize this. And then for my partition key, I'm going to put ID. And this is because, again, the application is set up to utilize this for organization within the table. And then I'm going to keep this type as a string. After I've done that, all of the default settings can remain, and I'll just go ahead and click Create Table. And that takes just a little bit of time, and the table will be created in just a bit. So I'll just give it a couple of seconds here. So that took almost no time at all, and the table has successfully been created. So now that the table is created, instead of adding items directly to this table, what I want to do is test the application again. So I will make sure I copy my instance's public IP address. So I'll go over to my instances and select the instance that was launched for this and copy its IP address. And then in a new tab, I will paste that address, and I can see that the employee directory app is still running, and it is currently an empty directory. But I can go ahead and add an employee to this directory just to make sure that everything is connected. So what I'll do is I'll click Add, and I'll go ahead and put my name here, and then my location, and my job title. I'll also just select a couple of these options here, just so that we can see what it looks like as everything is added to this table and added to this directory. So since I am a Seattle resident, I am also very much a Seattle fan, and I'm very definitely a coffee snob. I will also not just put this information into the table, but I will add a file. I'll add my employee photo and open that up. And then once that has all been added, I can go ahead and click Save. And as we can see, I now have an entry in the employee directory. So it looks good here, and we can see that I am now in the directory, but I want to show that this isn't just something that was added to this location. So what I will do is show that these items were added in the table and in the S3 bucket. So starting with S3, I'll go over to S3. And then I will open up the bucket that I had created. And as we can see, my employee pick has been added, and it's the employee picture that I uploaded. Even though it has its own designated name here, this is the object that was uploaded through that application. And then I can also go over to DynamoDB and can view my table, and view my employee table and explore the table items. And I can also see that my employee items that were added through the directory are here. And so it shows which badges I associated with myself, my name, my job title, my location. It shows the name of the object that was uploaded through the directory, and it shows the ID specifically for this table and the partition key that we established. So now that all of that has been done, what I want to do is just go ahead and keep the table running, but I want to go back to EC2 and stop the instance so that I'm not accruing any additional charges as I prepare to move on to the next stage of this application infrastructure development. So I'll go ahead and stop that instance, and that's where I'll go ahead and close this walkthrough out, and I'll see you in the next one.
Hello, everyone. Good to see you're here and ready to learn. You're almost done with the course. Now that we've added a storage and database layer, the employee directory application is fully functional, but we still have two more issues. The first issue is that we have no insight into how our application is performing and how it utilizes resources. So to fix this, we will start off the next lesson with a discussion of a monitoring tool called Amazon CloudWatch. After we understand what the demand for your application looks like, we'll address the second problem, scalability. You may find that your application demand isn't always constant, so in the last section of the course, you'll learn how to automate the process of adding resources as demand increases and reducing capacity as demand declines to reduce cost. You'll also learn how to deliver traffic and load balance across a changing amount of resources. Let's get started. When you have a solution built out of many different pieces, like how we build solutions on AWS, it's important to be able to see how different services are operating over time and react to operational events as they are happening. Let's consider the employee directory application. It's Monday morning and the users are seeing latency on page loads. It's probably not good enough to wait until a user sees the slowdown, calls, or enters a ticket saying, "Hello, your application is running slow." If you receive a call or a ticket from your users, you can then react and troubleshoot the issue. Waiting for users to notice and report issues to investigate will generally lead to unhappy end users. Ideally, you'd be able to respond to operational issues before your end users notice. On top of that, the end user can only provide information about their experience, and they cannot give insight into the inner workings of your solution. So they can report the issue to you, but where is that issue coming from? Is it an EC2 problem? Is it a database problem? Is it a code change that has recently been deployed? Without monitoring, you have to do some digging to figure all of that out. So what do we need to do? The first step is to put proper monitoring in place. Monitoring is a verb. It's something we do. We collect metrics, we collect logs, we watch network traffic. The data needed to help you pinpoint problems comes from the different services and infrastructure hosting the application, and monitoring tools help you collect the data being generated by these systems. In a cloud environment that is ever-changing and ever-scaling, it's even more important to collect various types of information about the systems as they scale up and down and change over time. The different services that make up your solution generate data points that we call metrics. Metrics that are monitored over time are called statistics. A metric is a data point like the current CPU utilization of an EC2 instance, where other data you monitor could come from different forms like log files. For example, your network will generate data like flow logs so you can see how network traffic is coming into and out of your VPC. The servers will be generating metrics such as how much CPU is currently being used or how much network traffic the instance is accepting at any given moment. Then finally, one more example is your database layer, which will generate metrics such as the number of simultaneous connections to your database. So you need a way to collect all of this information. Once it's collected, it can be used to establish a baseline, and this baseline can be used to determine if things are operating smoothly or not. If the information collected deviates too far from the baseline, you would then trigger automatic alerts to go out to someone or something to try to remediate the issue. A good monitoring solution gathers data in one centralized location so you can proactively monitor and operate your system to keep your end users happy, as well as allows for automated tasks to be triggered based on the data coming in. This is where Amazon CloudWatch comes in. CloudWatch allows you to monitor your solutions all in one place. Data will be collected from your cloud-based infrastructure, so you can see things like database metrics coming from RDS or DynamoDB, alongside EC2 metrics, as well as metrics coming from other services making up your AWS solution. Coming up next, we'll dive into some CloudWatch features and use cases. In this video, I'm going to run through some of the features that Amazon CloudWatch has to offer. We've already deployed resources into our AWS account with the Employee Directory application. So to get a handle on what CloudWatch is and how it works, let's dive into the AWS console and see what we can see. The end goal of this demo is to set up a dashboard that shows us the CPU utilization of the EC2 instance over time and set an alert that will be sent out if the CPU utilization of the instance goes over 60% for a period of time. I'm already in the console and I will navigate to Amazon CloudWatch. A lot of the AWS services begin reporting metrics to CloudWatch automatically when you create resources. Let's explore what types of metrics are available from the resources that we have already created in a previous lesson. To do that, let's first create a dashboard. A dashboard in CloudWatch is a customizable page in the console that you can use to monitor your different types of resources in a single view. This includes resources that are spread across different AWS regions. I want to create a dashboard that shows me the CPU utilization over time for the EC2 instance hosting the Employee Directory application. So now I'm going to click Dashboards in the left-hand navigation, and then click Create a Dashboard, and we can then name this dashboard My Dashboard. AWS resources automatically send metrics to CloudWatch, and it's built into the service. I'm going to select which widget we can add to the dashboard, and I will select a line graph here. Next, we can take a look at what the data source will be for this widget, and I will select Metric for this. Now we can browse through all of the available metrics. This is organized by service, so I will find EC2. I will select EC2, and then I want to view per instance metrics. From here, I can scroll through the different EC2 specific metrics that are being reported to CloudWatch, and I want to select CPU utilization. Click Save, and now we are brought back to the dashboard with one line graph for one specific instance's CPU utilization. This gives us visibility into one aspect of the health of our EC2 instance. You can explore in your own account what other metrics are available for you through CloudWatch by default, but you can also report some custom metrics to CloudWatch programmatically. This is good to know because with EC2 and CloudWatch, you only get visibility into the health of the instance by default, which doesn't really give you a holistic picture of the health of your application. The application running on the instance might not be operating correctly, but the CPU utilization could be fine. So keep in mind that you may choose to use custom metrics to get a more detailed and accurate view of the health in these dashboards. Once a dashboard is created, you can then share it with your team members. Now let's move on to another feature of CloudWatch called Amazon CloudWatch Alarms. CloudWatch Alarms allow you to create thresholds for the metrics you are monitoring, and these thresholds can define normal boundaries for the values of the metrics. If a metric crosses a boundary for a period of time, the alarm would be triggered, and then you can take a couple of different automated actions after an alarm is triggered. In our use case, I want to notify someone if the CPU utilization spikes over 70% for a period of time, say 5 minutes. Let's create an alarm to do that. Let's navigate to the Alarm section and click Create Alarm. Now what I want to do is create an alarm for CPU utilization, so I will select Metric, click on EC2, Per Instance Metrics, and scroll down to select CPU utilization. Now I will select the time period we are monitoring to trigger the alarm, which in this case is 5 minutes. You want to make sure you pick a reasonable time period where you don't wait too long to respond, but you also don't respond to every short-lived uptick in CPU utilization. There is a balance to strike here, and it will be highly dependent on your specific situation and your desired outcome. Okay, so now I will scroll down and type in 70 for the static threshold which we are watching for, which is representing the CPU utilization threshold. If it goes over 70% for more than 5 minutes, it's likely that there's a problem. And now we will configure the action that will be taken if the metric triggers the alarm. For CloudWatch alarms, there are 3 states an alarm can be either in alarm, OK, or insufficient data. An alarm can trigger an action when it transitions between these 3 states. In our case, I want to have this send out an alert to an email address when it transitions from OK to in alarm. AWS has a service called Amazon Simple Notification Service, or SNS, which allows you to create a topic and then send out messages to subscribers of the topic. You can imagine a scenario where we have systems admins or developers on call for our employee directory application. And if something goes wrong, we want to send them an email paging them, letting them know that something is going wrong with the app. So we will select Create a new SNS topic since we do not have one in place already, name it CPU Utilization Topic, and then I will put in an email address here to receive the alert. Notice as I scroll down here that there are other actions you can take for a CloudWatch alarm. We will talk more about some of these options in upcoming lessons. So then click Next and give this a name and a description. And finally, click Create Alarm. It will take some time for the alarm to begin collecting enough information to leave the insufficient data state and transition into the OK state. That is it for now. We will continue to use CloudWatch in upcoming lessons to make our solution elastic through EC2 autoscaling.
At this point, you know how to set up alarms to notify you when your infrastructure is having capacity, performance, or availability issues. But we need to go one step further. We don't just want to know about these issues, we want to either prevent them or respond to them automatically. In this section of the course, you'll learn how to do just that. Currently, our infrastructure looks like this. We have one EC2 instance hosting our employee directory application in a single availability zone with DynamoDB as its database and S3 for storage of static assets. If I wanted to evaluate the availability of our infrastructure, I have to look at each individual component. I know that both DynamoDB and Amazon S3 are highly available by design, so that leaves one issue, this singular instance of our application. If that instance goes down, employees have no way to connect to our application. How do we solve this? Well, as you already know, to increase availability, we need redundancy. We can achieve this by adding one more server, but the location of that server is important. If instance A goes down, we don't want instance B to go down for the same reasons. So to avoid the unlikely event of, say, an AZ experiencing issues, we should ensure that instance B is put in another AZ. So now we have 2 instances that we've manually launched, but let's say our company grows rapidly and the employee directory application is constantly being accessed by thousands of employees around the world. To meet this demand, we could scale our instances vertically, meaning we could increase the size of the instances we have, or we could scale our instances horizontally, meaning we could add more instances to create a fleet of instances. If we scale vertically, eventually we'll reach the upper limit of scalability for that instance. But if we scale horizontally, we don't have those same limitations. I can add as many instances to my fleet as I'd like. But if I need, say, 15 more instances to meet demand, that means I'd have to manually launch those 15 instances and manually shut them down, right? Well, you could do it that way, or you could automate this process with Amazon EC2 autoscaling. This service will allow you to add and remove EC2 instances based off of conditions that you define. With this service, you can also maintain the health of your fleet of instances. But with more EC2 instances comes a bigger issue. How do we access those servers? Before, we were simply using the instance public DNS name or public IP address. But when you have multiple instances, you have multiple of IPs to route to. Instead of maintaining the logic to send requests to your various servers, you would use a load balancer to distribute those requests across a set of resources for you. And since you can connect from your load balancer to access the application, you no longer need to use the public IPs of your EC2 instances. Before the next video, I'll spin up 2 instances hosting our employee directory application. See you soon.
As more people visit our application, the demand on our 2 web servers is going to increase. At some point, our 2 instances aren't going to be able to handle that demand, and we're going to need to add more EC2 instances. Instead of launching these instances manually, we want to do it automatically with EC2 autoscaling. Autoscaling is what allows us to provision more capacity on demand, depending on different thresholds that we set, and we can set those in CloudWatch. Okay, so we're going to draw a high-level example of how this works, and then Ceph is going to build it for us. So, looking at our application, traffic coming in from the outside can come down to either EC2 instance. In this video, these EC2 instances will be part of an auto-scaling group. Each of the EC2 instances that we launch will be completely identical. Then we're going to run code to simulate stress on our employee directory application that will make the instances think that they're overloaded. When this happens, the instances will report to CloudWatch and say that their CPUs are overloaded. CloudWatch will then go into an alarm state and tell autoscaling, give me more EC2 instances. As each instance comes online, they will pass ALB health checks, they'll start to receive traffic and give us the horizontal scalability that we need. Ceph will be helping us build out the scalability. Let's have him join us. You got all that, right?
Yes, it's time to make this app scale. Let's make it happen. So to get this built out, the first thing we need to do is create a launch template. This is going to define what to launch. So it's all about setting the configurations for the instances we want to launch. Morgan said we want our instances to be identical, and that's what we'll be configuring here. First thing we're going to do in the EC2 dashboard is find launch templates on the side panel and click Create Launch Template. We'll first provide a name and description. I'll call this app-launch-template and give it a description of a web server for the employee directory app. Then you'll notice this handy checkbox that asks if we are going to use this launch template with EC2 autoscaling. We are, so we'll check it and scroll down. We'll then choose the AMI. Again, the launch template is all about what we launch. So what we want to do is create mirrors of the web servers hosting our app that we already have running. That way, whenever we scale out, we just have more instances with the exact same configuration. When we launched the instance hosting our app earlier, we used the Amazon Linux AMI and a T2 micro instance type. So we'll select both of those options. Next, we choose the security group for our new instances. We'll use the same security group you created earlier in the course, the web security group. Then we scroll down and expand the advanced details selection. Here we'll choose our instance role, the same role we used previously in the instance profile dropdown. Once we do that, we'll scroll all the way down and paste our user data. This is what grabs our source code and unzips it so that our application runs on EC2. Now we're done and we can click Create. Now that we've configured our launch template, which again defines what we launch, we now have to define an autoscaling group which tells us where, when, and how many instances to launch. To create an autoscaling group, we'll select autoscaling groups on the side panel and then create an autoscaling group. Here, we'll enter a name such as app-asg and then select the launch template we just created, app launch template, and then click Next. Then we'll select our network. We'll choose the same VPC we created earlier in the course, app-vpc, and select both the private subnets we created, private A and private B, and then click Next. We then need to select Attach to an existing load balancer to receive traffic from the load balancer we created earlier, and then choose our target group, App Target Group. Click Enable ELB Health Checks so that the load balancer will check if your instances are healthy, and then click Next. Now we'll choose the maximum, minimum, and desired capacity. The minimum we'll say is 2. This means that our autoscaling group will always have at least 2 instances, one in each availability zone. The maximum we'll say is 4, which means that our fleet can scale up to 4 instances. And the desired capacity, which is the number of instances you want to be running, we'll say is 2. Next, we can configure the autoscaling policies. With scaling policies, you define how to scale the capacity of your autoscaling group in response to changing demand. For example, you could set up a scaling policy with CloudWatch that whenever your instance CPU utilization or any other metric that you'd like reaches a certain limit, you can deploy more EC2 instances to your autoscaling group. So, what we want to do is use target scaling policies to adjust the capacity of this group. Earlier, Morgan created a CloudWatch alarm that resulted in the action of sending out an email. Here, we're going to create a target tracking policy, much like Morgan created the alarm, but this time it will result in the action of triggering an autoscaling event. So we'll name this CPU utilization, and then we'll say that we want to add a new instance to our fleet whenever the target value is 60%. We'll also keep the instance's need setting at 300 seconds to warm up before scaling. Then we'll click Next to configure notifications when a scaling event happens. This is optional, so for now we're going to skip past it. All right, here we can review and click Create Autoscaling Group. Now all that's left is to stress our application and make sure that it actually scales up to meet the demand. To do that, I'll open up a new tab and paste the endpoint for our Elastic Load Balancer. Here's our application. I'm going to go to the info page by appending /info on the URL. You'll notice here that we built in a stress CPU feature. This is going to mimic the load coming into our servers. In the real world, you would probably use a load testing tool, but instead we built a stress CPU button as a quick and easy way to test this out. Then we can watch our servers scale with that autoscaling policy. So, as the CPU utilization goes up, our autoscaling policy will be triggered and our server groups will grow in size. I'm going to select 10 minutes for our stress test. All right, some time has passed. We've stressed our application, and if we take a look at CloudWatch, we can see what happened. So let's click on CloudWatch. If you look here, we can see our alarm summary. We went over 60% CPU utilization across instances. That was our threshold, so we launched new instances. We launched 2 new instances into our autoscaling group. Then you can see the loads start to come down. Because we've launched more instances into our autoscaling group, there were more hosts to accept traffic for our Elastic Load Balancer, and the average CPU utilization went down across servers. All right, let's go look at the EC2 instances that were launched into the autoscaling group. I'm going to go to the EC2 dashboard. From here, I'm going to scroll down to Target Groups and select the App Target Group. I'm going to select Targets, and we can now see that we have 4 healthy target instances in our autoscaling group. So now we have an environment with an autoscaling group and our launch template. We've set up an alarm in CloudWatch that whenever our CPU utilization goes over 60%, we're going to launch more instances into that group. All right, and this app should be able to scale now using EC2 autoscaling.
Great, thank you, Steph. All right, now, if we wait around long enough, what we would see is as the CPU load dropped off, then one by one, they would each get terminated because we no longer need them, bringing our state all the way back down to the basic 2 we need, the minimum number for this particular group. All of that done without any human interaction. If for some reason you are doing this in your AWS account, don't forget to delete the autoscaling group instead of the instances. Otherwise, guess what will happen? The autoscaling group will spin up more instances to replace the ones that were deleted. So ensure you are deleting the autoscaling group as well. If you've been watching the latest tech releases recently, you may have noticed a common theme: artificial intelligence. Across the industry, there have been some really exciting announcements around AI, and more specifically, generative AI.
It's important as someone working in or around the tech industry to stay up to date with the latest trends and innovations, even if it's not yet currently impacting your day-to-day. Especially when it comes to AI, we are really at the beginning of the journey, and getting a handle on what generative AI is and what types of tech are coming out and how to use them will take you a long way when these technologies begin to work their way into your everyday life. In fact, millions of people around the world are already using generative AI applications in meaningful and exciting ways, like interacting with virtual assistants, creating applications for fraud detection, working with customer service chatbots, integrating code generation into the software development process, and much more. Chat applications are a very common example of applications using generative AI. The way generative AI chat applications work is you provide an input to the model as a natural language prompt, like pretend you are my teacher, explain to me what generative AI is, and then the model responds with a generated output, which in this case is text that is explaining generative AI to you as if it's your teacher. Generative artificial intelligence, generative AI, or Gen AI is a type of AI that can create new content when prompted to do so. And this content is based on the data the underlying model was trained on. The generated content can include conversations, stories, images, videos, music, and more. When you're learning about generative AI over the next few short videos, you will hear about terms like large language models, or LLMs, and foundation models, or FMs. Let's define these terms. LLMs, which are an application of generative AI, are specifically designed for tasks revolving around natural language. LLMs are trained on very large data sets, which makes it possible for the models to be used for tasks related to language processing and comprehension. LLMs are also capable of generating text that simulates natural language based on their training data. In short, LLMs are great for language-related tasks like writing, summarizing, translating, and more. Foundation models, on the other hand, are massive machine learning or ML models that are initially pre-trained for general purpose and should be fine-tuned with local data to be better at specific tasks that require more of a specialized knowledge. To summarize, FMs are base models. They're pre-trained and ready, but they probably need a bit more fine-tuning to become experts in whatever specific areas you need them to be experts in. All right, now that we have some context, let's talk about an exciting service from AWS called Amazon Bedrock. Amazon Bedrock is a fully managed service that you can use to access a variety of high-performing FMs through application programming interfaces or APIs. Through Amazon Bedrock, you can access and use FMs from leading AI companies. Some examples of providers of these models at the time of this filming include Amazon, Anthropic, Cohere, Meta, and more. These models do differ in their capabilities and specialties, and you'll want to choose the right one for your specific use case. Using Amazon Bedrock, you can easily experiment with and evaluate the foundation models and see which one is the best fit, because getting started is just a few API calls or clicks away. No need to create your own model to get started. One of the categories of models offered through Amazon Bedrock is the Amazon Titan family of models. Amazon Titan models are FMs that AWS has created that are general purpose and can support a variety of use cases. One of the benefits of the cloud is that it's way easier to experiment and evaluate technology to find the best fit without getting locked into any early technology decisions. So you can run some experiments of your own with the available models to see which one works best for you. Now remember, these are foundation models, which means you'll likely want to fine-tune them to your needs. You can fine-tune these models to create custom models. To fine-tune a model, you have some options. You can create a continued pre-training model, which means you can train a model with new unlabeled data, or you can fine-tune a model, which means you can improve a model's performance on specific tasks by providing a training dataset of labeled examples related to that task. You can also create what are called knowledge bases by uploading your own custom data sources that create a repository of information that are then used to augment a foundation model's responses, or it can be used to augment prompts.
This allows you to reference proprietary information in your generated responses, and it uses something called Retrieval Augmented Generation, or RAG, to achieve this. RAG is a technique that fetches data from company data sources and enriches the prompt to provide more relevant and accurate responses. In this case, the company data source connection with Bedrock is facilitated through the knowledge base. Using RAG is also a technique that can help reduce AI hallucinations, which is when the AI-generated output includes information that is inaccurate or fabricated. Behind the scenes, this is using something called a vector database to store and manage the data, and the models use vector databases as an external data source to improve their capabilities. A vector database is optimized for handling and retrieving data in the form of vectors, which are numerical representations of information. By converting textual data into vectors, the knowledge base can efficiently search and retrieve relevant information using similarity searches. This then makes it possible for the foundation model to access and incorporate specific data points from the knowledge base. Now, that's some of the technical details around customizing models, but getting started with Amazon Bedrock is actually pretty simple. Amazon Bedrock is serverless, so you can get started, securely customize foundation models with your own data, and securely integrate and deploy your models into your applications using AWS tools without having to manage any infrastructure. Because of this serverless experience, you can actually explore Amazon Bedrock directly in the AWS Management Console. This is helpful for getting a feel for what these models can do before you start integrating them with your applications using the API. In the Amazon Bedrock console, in the navigation pane, there is a header called Playgrounds, and there are multiple types of playgrounds that you can experiment with. There is the Chat Playground, where you can select a model and experiment with it to see how it works. For example, if we choose Select Model, we can then view the different models available. I'm going to select the Amazon Titan Text G1 model and then start a chat. I'm going to make a simple prompt here just as a proof of concept. I'll enter write a short Python script to read local files from a directory and upload them to Amazon S3 and choose Run. Then a response is generated and displayed on the screen, including some sample code I can review and potentially use for my project. Because this is the chatbot playground, I can also iterate on this script with the chatbot, change model configurations, or I can practice my prompt engineering skills and iterate on my prompt to get the desired output. There's also a text and image playground available through the console. After you're ready to begin building applications with Amazon Bedrock, it's relatively easy to integrate generative AI capabilities into your applications. You don't need to build and train the models from scratch, as you've seen. They already exist, and you can use them by customizing your models as you see fit, calling the Amazon Bedrock APIs using the AWS SDKs and providing the correct parameters. All right, so that is a light introduction to Amazon Bedrock. I hope this gave you a good overview of what it offers and how it can benefit your projects. There are more generative AI services AWS offers as well, like Amazon Q, for example. Make sure to check out the AWS documentation to learn more about these generative AI offerings.
Now that we have multiple EC2 instances hosting our application in private subnets, it's time to distribute our requests across our servers using the Elastic Load Balancing, or ELB service. Conceptually, how this would work is a typical request for the application would start from the browser of the client and is then sent to the load balancer. From there, the load balancer determines which EC2 instance to send the request to. After it sends the request, the return traffic would go back through the load balancer and back to the client browser, meaning your load balancer is directly in the path of traffic. Now, if we're looking at the architecture, the ELB looks like one thing. It looks like a single point of failure. But ELB is actually, by design, a highly available and automatically scalable service, much like S3 is. What that means is that A, the ELB is a regional service, so you don't have to worry about maintaining nodes in each availability zone or having to configure high availability yourself. AWS maintains that for you. And B, the ELB is designed to handle additional throughput and will automatically scale up to handle the traffic coming in, without you having to configure that feature. Now, there are several types of load balancers that you can choose. There's the application load balancer. That load balances HTTP and HTTPS traffic. There's the network load balancer that routes TCP, UDP, and TLS traffic. And there's the gateway load balancer that is mainly used to load balance requests to third-party applications. For our employee directory application, we'll be load balancing web traffic, so we'll be using the application load balancer, or the ALB. When you create an ALB, you'll need to configure three main components. The first component is a listener. The goal of the listener is to check for requests. To define a listener, a port must be provided as well as the protocol. For example, since we're routing web traffic and we set our application to use port 80, we'd want our load balancer to listen to port 80 using the HTTP protocol. Additionally, we could set up a listener port for 443 using the HTTPS protocol. The second component is a target group. A target is the type of backend you want to direct traffic to, such as an EC2 instance, AWS Lambda functions, or IP addresses. A target group is simply just a group of these backend resources. Each target group needs to have a health check, which is how the load balancer can check that the target is healthy so that it can start accepting traffic. The ALB operates on the application layer, which is layer 7 of the OSI model. This gives the load balancer a lot of cool features, and one of those is the third component, which is a rule. A rule defines how your requests are routed to your targets. Each listener has a default rule, and you can optionally define additional rules. So if we had two target groups, A and B, we can set up an additional rule that says if traffic is coming to our /info page, we can deliver that traffic to target group B. So because of the fact ALB operates on layer 7, you can customize paths for your traffic. Okay, now it's time to put this in practice. Let's create an application load balancer in the console. If you want to find the ELB service, you'll need to go to the EC2 console. So we'll type in EC2 to the service search bar, and then on the side panel, we'll select load balancers. Once we bring up our load balancers dashboard that shows all of the load balancers for this region, we'll then click Create Load Balancer. Here's where we choose which type of ELB we want, and you see the three main types. We'll be using the ALB. From here, we'll choose a name and call it app-ELB. The next setting asks if we want an internet-facing or an internal-facing load balancer. An internet-facing load balancer does what you might expect, which is route requests from clients over the internet to your backend servers or targets. An internal load balancer, on the other hand, will route requests from clients with a private IP to targets with a private IP. For example, if you had a 3-tier application with a web, app, and database tier, you could use an internal-facing load balancer to route traffic from your web tier to your app tier. For this app, we'll be routing internet traffic, so you can leave it as internet-facing. After that, we choose which availability zones we want to route traffic to. First, we'll choose the VPC, select both availability zones, and then choose the two public subnets. Now you choose your security group for your load balancer. This is where you decide which traffic you want to allow in. Here, we'll choose a security group that will allow traffic on port 80 from anywhere. Then, we configure the listeners and routing. Currently, the default setting is to allow HTTP traffic on port 80. If we want to allow or limit to HTTPS traffic, we can click Add Listener and choose HTTPS, but for this demo, we'll stick with the default. Next, we'll configure routing, and for this, we need to click on Create a Target Group. This will open a new page where we can configure the target group. First, we will select the target type, which will be instances. Then we can scroll down and we'll give it a name, such as app-target-group, and leave all of the defaults selected. Then we'll click Next to choose which instances we want to live in the target group. For here, I'll choose the 2 instances I've created in private subnets and click Include as Pending below. And click Create Target Group. Now, coming back to the load balancer creation page, if we refresh the dropdown for target groups, we'll see the target group that was just created. We will select this and then scroll down, accepting the rest of the defaults and clicking on Create Load Balancer. After the load balancer has been created, we can then select it and find the DNS URL in the description box. We can then pull that DNS URL, copy and paste it into a new tab, and from here you can see our app. If I go to the /info page of our app, you can see which availability zone we're currently in. If I refresh the page a few times, you should see eventually that I'm being directed to both my EC2 instances in both AZs.
All right, one more lab, and this time we're going to make the employee directory application highly available. In this lab, you will first review an Amazon EC2 instance and validate its configurations. Then, using this information, you will create a launch template which will be used for EC2 autoscaling, and you will create an application load balancer. Next, you will set up an autoscaling group using the launch template. This will enable your application to scale in and out with demand. Then you'll need to test it all out. The application has a stress feature built into it, which is used to simulate demand. You'll use this stress feature and then validate that scaling did actually occur. All right, go ahead and get started.
Hey y'all, and welcome to our final exercise walkthrough where we handled the load balancing and auto scaling for our application. As you can see, I am already logged into the AWS Management Console, and I'm using the admin user that I created earlier in order to handle these tasks. So in order to set up our load balancing and auto scaling, the first thing I'm going to do is launch the application instance. So I'm going to go over to EC2 and then go over to my instances and work with the last instance that I created. In this case, it's the employee directory app DynamoDB. So I will select that and I will go ahead and use the shortcut that we've been using where I click Actions, Image and Templates, and then Launch More like this. In this case, instead of appending DynamoDB, I am going to append LB for load balancing for this instance. And then I'm just going to scroll and make sure that everything is where I want it to be. So I want to make sure I continue using the same key pair. And then I also want to make sure that I enable the public IP so that I can access and test this instance. From there, I'm going to scroll down to the advanced details again, just to double check that my instance role is still selected and that my user data is where I left it. And from there, I'll go ahead and click Launch Instance. And now that that instance is launching, I can go over to View My Instances, and I will just give this some time to go ahead and be fully launched so that we can make sure that the instance is up and running and that the application is ready to go. All right, now that it has been a few minutes, I'll go ahead and click refresh again. And it looks like 2 of 2 checks have passed for this application instance. So just to verify that the application is up and running, I'll copy that IPv4 IP address and then paste that into a new tab. And it looks like our employee directory is up and running. And because it does have access to the S3 bucket and DynamoDB table that were created, the data that I had already added to the directory is still going to be visible, even though this is a new instance. So now that I've verified that that works, I can go ahead and close that. And what I want to do next is to create the application load balancer. So to do that, I do need to be in the EC2 console because the load balancers are accessed through the EC2 console. So the way that I get to the load balancing is I scroll down in this side navigation pane, and then there's this section near the bottom that says load balancing. What I want to do is click load balancers, and now that I'm in the load balancers page, I will go ahead and click create load balancer. And the type of load balancer that I want here is an application load balancer. So under that option, I will go ahead and click create. For my load balancer name, I want to go ahead and put in app-elb. And then I do want to make sure that this is an internet-facing load balancer so that I can access its endpoint from the internet. After that, I'll go ahead and scroll down, and under network mapping, I need to make sure that I select my app VPC because that is where my instances are launched. That's where my instances for this application will be launched. And then for the availability zone mappings, I want to select both US West 2A and US West 2B. Once those are selected, you can see that it pops up with the ability for me to specify which subnets I want to route within, and I will go ahead and keep that with the public subnets for those availability zones. So scrolling down, I get to security groups, and what I want to do here is just make sure that proper access is set up for my load balancer. So to do that, instead of using this default security group, I'm going to go ahead and click create new security group, and that will take me to a page where I can do just that. I can create a new security group. So for this, I'm going to name it load balancer SG, and then my description is just, this is for HTTP access. The VPC for this needs to be my app VPC, so just making sure that that's the one that is selected. And then I want to work with my rules. So currently it has no inbound rules, so I'll go ahead and add a rule and then add HTTP access from anywhere. And from there, I will go ahead and create my security group. So now that that security group has been created, I can close out that new tab and then refresh my security group list. And now I have the ability to select the security group that I just created. And that will be the security group that I use for this load balancer. Now that that's been done, I'm going to scroll down to listeners and routing. And this is going to be where I determine how my load balancer is receiving requests and how it's forwarding those requests on. So here I'm going to click create target group, and that will open up a new tab. I want to keep instances selected as the target type, and then I want to name my target group app target group. After that, I want to make sure that it's associated with the correct VPC, and then I want to scroll down to health checks, and health checks is going to be how the load balancer determines which instances are capable or which targets are capable of receiving requests. Here I want to expand advanced health check settings, and I want to make my healthy threshold 2 and my unhealthy threshold 5. I also want to make my timeout 30 seconds, and I want to change the interval of checks to 40 seconds. So what this does is the healthy threshold is how many consecutive health checks that are successful are going to determine if the instance or if the target is available to receive requests. An unhealthy threshold is how many consecutive failed health checks determine which targets are not available to receive requests. For the timeout, this is just how long is it going to take for the health check to fail if no response is received. And then the interval is just how often are the health checks going to be sent. With all of those selected, I'm going to go ahead and scroll down and then hit next. And now I am able to register targets to my target group that I am creating. For this, I am going to go ahead and select the instance that I had just launched to include as a target, and then I'm going to select include as pending below. Now that that has been included, what's going to happen is I will create the target group, and then the load balancer will start those health checks to make sure that that instance as a target is up and running. So I'll go ahead and click Create Target Group. And that target group has been created. So since that target group has been created, I will go ahead and close this tab. And back on my load balancer creation page, I can go ahead and refresh my listeners and routing drop-down list, and I can select App Target Group, which I have just created, in order to be utilized by the load balancer. Once I've selected that, I can scroll down and click Create Load Balancer. And now that the load balancer is being created, I can click View Load Balancer. And as you can now see, I have a load balancer that has freshly been created, and it is just currently being provisioned, and that will just take a couple of minutes. So after a couple of minutes, we can see that the state of the load balancer has changed to active. So what I want to do from here is just test to make sure that I can access my application from the load balancer. So to do that, I will select this specific load balancer, and what I want to do is copy the DNS name for this load balancer. With that copied, I will go ahead and open up a new tab, paste that load balancer endpoint in there, and as we can see, the load balancer is directing traffic to the application instance with the data that I have added. Okay, now that I can see that that works, I'm going to go back to the EC2 management console, and the next thing that I want to do is get everything ready for scaling. So the first thing that I need to do in order to do that is to create a launch template. So in the left-hand menu here, under instances, there's a selection for launch templates. I'm going to go ahead and select that. And because I don't currently have any launch templates created, I will go ahead and click Create Launch Template. My name for this will be App Launch Template, and my description will just be a web server for the employee directory application. From there, for auto-scaling guidance, I want to select this because I am specifically going to be focusing on EC2 auto-scaling. And then I want to scroll down and select the components that are necessary for me to launch my instances. What the launch template does is just it tells autoscaling what it is that I want to launch. So what instances, how to configure those instances, and all of the details that you would use if you were manually launching instances. So what I can do here is, since I do have instances already running, I can select currently in use, and that will bring up what I am currently running. And because my account only has one instance currently running, it will pull the information for that instance. For my instance type, I want to select a T2 micro because that is the instance type that I want to scale, and it's free tier eligible, so that will keep those costs down for this little exercise. For my key, I'll just keep selecting the same keys that I have been. And then for my network settings, I want to make sure that I select the security group that I created specifically for this. And so that is going to be my web security group. After I've done that, I'm going to go ahead and scroll down to my advanced details and expand that. And the two main things that I want to do here are I want to make sure that my instance profile is utilizing the role that I've set up for access to the other resources. And then I want to make sure that I add my user data in order to install and configure the application that I'm using. So to do that, I will go ahead and paste the user data in here. But then I just need to make sure that I change the necessary components so that I am working with the same resources. So I'll change my bucket to the bucket that I've created for this application, and I will change my region to US West 2 for the Oregon region. So once I've done that, I can create my launch template. And as we can see, my launch template has been successfully created. And if I go over to View Launch Templates, I can see the newly created launch template. From here, I need to create the actual auto-scaling group. So to do that, I am going to scroll down in this left-hand navigation pane, and under auto-scaling, I'm going to select auto-scaling groups. I don't currently have any auto-scaling groups, so I will click Create Auto-Scaling Group. The name for this group will be App ASG, and because I've created a launch template, I can go ahead and just select the launch template that was created specifically for this group. Once that has been selected, I can go ahead and click Next. And this is where I get to choose various launch options. So in this case, I want to make sure that I am launching into my app VPC, and then I want to launch these instances into my public subnets. So I will choose public subnet 1 and public subnet 2. With those selected, I can go ahead and click Next. And now I'm in my advanced options. The reason that this is important is because, for one, I've created a load balancer and I need to make sure that this auto-scaling group is utilizing that load balancer. So what I can do is attach to an existing load balancer, and then I can choose my load balancer from my load balancer target groups. From here, I can just drop this down and select App Target Group. And then for my health checks, I will just have the load balancer handle the health checks since those have already been set up. After that, I will click Next. And here is where I can decide how large and how small I want my group of instances or my fleet of instances to be. So what I'm going to do here is I'm going to change my desired capacity to 2. I also want my minimum capacity to be 2, and then I want my maximum capacity to be 4. This will mean that my auto-scaling group will launch with 2 instances, and then it will never get smaller than 2 instances. So if one of those 2 instances is deemed unhealthy, it will launch an instance to replace that. If there is a load on the load balancer and a load on the instances, then the maximum size that my fleet will be is 4 instances. And so that's what this group size is establishing. After that, I want to make sure that for my scaling policies, I choose a target scaling policy. And for this target scaling policy, I can change my target value for my average CPU utilization to be 60. And I'll keep the 300 seconds of warm up as the default. And that's just going to make sure that if I scale, the scaling is going to be based on my average CPU utilization across my fleet. And if that hits or goes above 60%, then it will launch new instances, but it will give those instances 300 seconds or 5 minutes to warm up and start passing their health checks before it does another scaling action. So now that that's done, I can go ahead and click Next. And for notifications, I am not currently going to add notifications for my walkthrough, but here you could add a notification and make that notification an SNS topic and utilize your email address so that you can be notified anytime a scaling action is taken. But instead, I'm just going to go ahead and click Next, and then Next again, and just quickly review that everything is where I want it before creating my auto scaling group. So now that my auto scaling group has been created, I need it to get everything to that desired capacity. And once it's there, I can test and make sure that my application is still accessible, and then I can test scaling. So before I test my application, what I want to do is go back to the EC2 console, and then under load balancing near the bottom of the left-hand menu, I want to hit target groups. The reason I'm doing this is that I want to make sure that before I start testing anything, that everything is running and is healthy. If I want to keep an eye on it, what I can do is click targets, and then as you can see, the auto scaling group has launched 2 additional instances, one in each availability zone, and they are currently healthy. So that means that my application is up and running, and I have multiple instances now that will be utilized whenever requests are made. And so if one were to become unhealthy or go down for any reason, I have the other instances there to still answer those requests. So to test my application and the scaling of the application, what I'm going to do is go back to the application page that I have open, and there's a stress test built into this application just to make it easier for this exercise. So what I'll do is append /info to the end of my URL, and that will take me to the page that allows me to handle some tooling. One of the things I can do is I can refresh this page, and it, as you'll see, it will go between the various instances that I have running and the availability zones that those instances are running in. So refreshing this will show that it's changing the instances and changing the availability zones that are being hit. But what I want to do to test this is utilize this stress CPU built-in test here, and I'm going to go ahead and stress the CPU for 10 minutes. So this is going to allow me to stress my CPU to get it above that 60% threshold and launch new instances. And so while I'm waiting for that to happen, I'm going to go back over to the target group and view my targets, and then I'm just going to periodically refresh this to see when new instances are being added and when they're healthy. So I'm just going to give that some minutes as I wait for those to launch. So now that I've given it some time, I'm going to just see if some new instances have been launched. So I'm going to go over to instances, and as I can see, 2 more instances have been launched in response to the scaling action that is happening because of the CPU stress that we initiated. So these instances will be launched, and then they will be added to the group of instances that are part of the entire fleet. I hope you enjoyed the course and that the exercises were helpful to you, and I'll see you in another course.
Nice work getting through this course. Let's take a look at how this architecture we built turned out. The employee directory application is currently being hosted across multiple EC2 instances inside of a VPC in a private subnet. These EC2 instances are part of an EC2 auto-scaling group, and traffic is being distributed across them using an application load balancer. The database is being hosted on Amazon DynamoDB, and the images are stored in S3. Beautiful. Looking at this from a maintenance perspective, you would need to ensure that your auto-scaling policies are working well with your expectations, and it would likely take some tweaking over time. You also would need to install security patches and updates for EC2, as well as keep an eye out for new instance sizes or types that might help you further optimize your solution. Now, this is really great, but as with everything built on AWS, there are multiple ways you can architect a solution and have success. It really depends on what you are optimizing for and what you are trying to do that will determine how you architect an application. That being said, what I want to do now is present to you an architecture that could be a wonderful serverless redesign of the employee directory application, taking full advantage of cloud-native services like AWS Lambda. I'm going to touch on some services we haven't covered yet in this course to give you ideas of alternative architectures. So, this employee directory application is a great example of a standard 3-tier application where you have the presentation layer, the application layer, and the data layer. The presentation layer is the user interface, the application layer is the business logic, and the data layer is the database. As things are right now, the Amazon EC2 instances are hosting both the presentation layer as well as the application layer. This is true because the EC2 instances have a web server running that is serving the content for the website, like the HTML, CSS, and JavaScript, which is the presentation layer. Then the same instances are also handling requests for the backend logic for viewing, adding, updating, and deleting employees, which is the application layer. What I want to do now is separate those two pieces entirely, having the front end of the website hosted separately from the backend application logic. It's important to separate the presentation layer from the application layer so that the instances are not overloaded by handling different types of requests at the same time. We're going to move the presentation layer to be hosted out of Amazon S3. S3 supports static website hosting, and therefore this is a great place for us to host the HTML, CSS, and JavaScript for our website. When you're hosting a static website with S3, you may think, well, my website isn't static, it's dynamic. It's pulling data from a database, so this isn't a static website, and therefore S3 would not work for this use case. This is where JavaScript comes in. JavaScript files have the ability to make HTTP requests and load dynamic content, modifying the static page to display results that come back from requests. So this should work well. The presentation layer is taken care of. Now I want to tackle the application layer. It used to be hosted on Amazon EC2, but let's go ahead and change this to AWS Lambda. This means that our employee directory application code would only be run in response to events being triggered by the front-end presentation layer. Now, you don't want your front end talking directly to your back-end code, so you would instead expose your back-end using an API. We would use the service Amazon API Gateway to host this API. Each action you could take on an employee would have its own method on the API. This API hosted on API Gateway would act as a front door to trigger the backend code, which we would host on AWS Lambda instead of EC2 as discussed. We could have one Lambda function handle all of the requests for employee data, or we could have one Lambda function for each action. We would keep DynamoDB for the database or the data layer, and we would also keep S3 for the employee photo storage. All of the access between these services would be handled via role-based access using IAM roles. One nice thing about this is notice how, because we built this solution in a modular way, we were able to swap out how we were handling the presentation and application layer while leaving the data layer totally intact with no modifications. That is the type of flexibility that can help you innovate and adapt quickly to changes. So now, for completeness and clarity, let's focus on the new architecture and fill it out a bit more. I will add some other AWS services to this diagram that you can explore on your own. First, I'm going to add Amazon Route 53 for domain name management and Amazon CloudFront here as well, which will allow us to cache those static assets like the HTML, CSS, and JavaScript closer to the end users by taking advantage of AWS Edge locations. If a user wants to visit the Employee Directory application website and view all of its employees, here's the flow. The user would first type in the domain for the website, which would get sent to Amazon Route 53. Route 53 would send back to the client the address of the static website being hosted on S3, and then the website would be rendered in the browser. This website has JavaScript making the API calls to the backend to load the dynamic content. So the API call to load all of the employees would be made, and it would hit API Gateway first. API Gateway would validate the request and then trigger the backend Lambda function. The Lambda function would then send an API call to DynamoDB to query the employees in the table, and it would return that data to API Gateway, which would then be returned to the JavaScript, which would finally be rendered on the page. All right, and that's that. With this architecture we just laid out, we have optimized for scalability, operational overhead, and depending on your usage, it could also be optimized for cost. The serverless aspects of this make the operations for support much less than compared with Amazon EC2-based workloads. There is no patching or AMI management when you use serverless solutions like AWS Lambda. Also, notice how it was not required that I create a VPC, subnets, security groups, or network access control lists for this solution. The networking aspect of this is managed for you, though you can integrate serverless services with your VPC if you need to for compliance reasons, but it's not required to get a solution up and running. You have many options to choose from when designing your application. You can imagine a scenario where you redesign the same application to be hosted using AWS container services, and then this entire diagram would change again. There are a lot of ways you can build on AWS, and that's the beauty of it. You can swap certain pieces of your solutions out as AWS services are released or gain new features. And because everything in AWS is an API call, you can automate the process along the way. That's it for this course. From me, Seth, Meowsy, and Fluffy, thank you so much for learning with us. One more reminder to please remember to delete any resources that you've created in your own AWS account for this class to avoid incurring any costs if you've been following along. Thanks again, and see you next time. Wouldn't it be nice if when you were coding, you had an always online, always available companion helping you along the way? With generative AI, you can have a helpful virtual coding buddy right in your integrated development environment or IDE. I'm talking about Amazon Q Developer. Amazon Q Developer is a generative AI-powered coding assistant that provides support during your software development process. Amazon Q Developer can chat with you about code, provide inline code suggestions, generate brand new code, scan your code for security vulnerabilities, and even help you make code improvements like language updates, debugging, and code optimizations. Amazon Q Developer is a general-purpose tool, meaning it can help you with general coding tasks, but it also has been optimized for AWS services and is an AWS expert. You can use Amazon Q Developer through the Amazon Q extension in your IDE and log in with a Builder ID. There are multiple ways to interact with Amazon Q Developer. The first we will cover here is through the chat interface. The chat interface is located in the IDE through the Amazon Q extension and is really useful because you can have a conversation about your code. You use natural language to interact with Amazon Q Developer, and behind the scenes, it's powered by Amazon Bedrock, which provides API access to foundation models supporting generative AI use cases. So, using natural language, you can ask Amazon Q Developer to help you with things like code suggestions or improvements, getting answers for general questions about building software, helping you figure out AWS best practices and general information, and you can even get assistance completing tasks like debugging, testing, and optimizing your code. When you start interacting with it via chat, it keeps track of the conversation within a given session as context. This means that you can ask follow-up questions or refer to previous questions and responses throughout the duration of your session. It can really be a great virtual assistant when you're working on projects. I myself use it to help me generate ideas, code, and debug issues as I'm programming. Think about how many times you've forgotten the syntax for a common task, or maybe you don't know the syntax for how to interact with a specific AWS API. With Amazon Q Developer being trained as an AWS expert, you don't need to leave your IDE to search the internet to get answers. Instead, you can simply ask Amazon Q Developer and get answers directly in your IDE. This helps you stay focused and on task, and you can quickly go from idea to implementation. Something else I love about having this tool in your IDE is that you can highlight code and then ask Q to explain the selected code, and it will do just that. It will explain the code to you line by line. There's a joke in software development where sometimes we are writing code and we may say, "My code doesn't work and I don't know why." Or even scarier, "My code does work and I don't know why." Asking Amazon Q Developer to explain the code can help you get an outside perspective without needing to go track down your coworker or do a bunch of research to help you better understand something. This is super useful for all developers, new and experienced. The other way to interact with Amazon Q Developer is inline when you are writing code. It can generate coding suggestions to you in real time as you type. These coding suggestions may be single line or full function code, and it can really help you accelerate how quickly you can build software. The way this works is that you can write a comment in natural language that outlines a specific task in English, such as upload a file to Amazon S3 with server-side encryption. Based on this information, Amazon Q Developer recommends one or more code snippets that you can accomplish the task with directly in the IDE. You can then optionally accept that suggestion or cycle through other suggestions. That being said, it's not just about simple code generation. You can also have it generate more complex code like full functions, and with that, it can help you solve problems quickly and efficiently through its code suggestions. Amazon Q Developer suggestions are based on large language models trained on billions of lines of code, including Amazon and open source code, and it uses your content, such as code snippets, comments, cursor location, and data from files open in the IDE as inputs to provide code suggestions. You can also customize Amazon Q Developer inline code suggestions, which means that it can make code suggestions that conform to your team's internal libraries, codebase, proprietary algorithmic techniques, and enterprise code style. Amazon Q Developer also has a feature where it scans your code to detect hard-to-find vulnerabilities and gives you code suggestions to remediate them. This can help you align to best practices for tackling security vulnerabilities, like those outlined by Open Worldwide Application Security Project, or OWASP, or those that don't meet crypto library best practices or other similar security best practices. You can also use Amazon Q Developer on the command line and have it provide IDE-style completions for hundreds of popular command line interfaces like Git, NPM, Docker, and AWS. So, with all of that being said, with Amazon Q Developer, you can be more productive, improve your code, enhance your code security, and have a clearer understanding of what your code is doing. All right, enough talking about this awesome tool. Stick with me, and in the next video, you will see Amazon Q Developer in action. All right, welcome back. It's time to see what Amazon Q Developer is all about. So let's hop into a demo to see this service in action. I am in my JetBrains PyCharm IDE, and I already have the Amazon Q developer extension installed under the Developer Tools section. I am also already logged in with my Builder ID, so we're ready to go here. First, let's explore using the chat interface. I'll start by selecting Amazon Q in the lower toolbar, which opens up a drop-down showing options I have for interacting with Amazon Q. I will then select the Open Chat Panel option, which opens up a chat for me to begin working with Amazon Q. I have an example code file open here for an AWS Lambda function that checks the certificates for a list of domains and returns whether the domains have valid certificates or if they are expired. I am going to not select any specific code yet, but I will ask Amazon Q, explain what this code is doing, and then submit my question. Amazon Q will generate the answer, which will take a few seconds. We can now review the answer Amazon Q provided. Amazon Q correctly analyzed this code and provided a detailed answer to what this code is doing. Using Amazon Q in this way can help you get up to speed faster with a code base, but I can also highlight specific code lines and ask it to explain that too. So if I select these lines here, and then I ask Amazon Q, explain the selected lines of code in detail, and then hit submit, Amazon Q will then generate an answer. Scrolling to the top of the answer, we can then scroll through to see what Amazon Q said. We won't read the answer in full detail together, but you can pause the video if you're curious about the level of depth Amazon Q provides. Amazon Q provides some interesting insights, and I find that using it even for simple use cases like this has made me a better developer. You can also ask Amazon Q to help you improve your existing code. I can ask it, what could I do to improve this code based on basic coding best practices, and submit my question. Amazon Q has come back with a number of suggestions to improve this simple code snippet that are specific to this example. Now let's use Amazon Q to help refactor the code. I want to change this code to read the list of domains from an environment variable instead of hard coding the values. To do that, I'll ask, I want to refactor this code to read the domain list from an environment variable instead of hard coding it. Can you help me refactor this code? And then I will submit my question. Amazon Q will then generate an answer. And Amazon Q has responded with a rewrite of the script using the new requirements. And it even added a couple of extra changes to improve the code as well, like error handling. You do have the option to insert this code at your cursor, but in this case, I will copy the code, then replace the script in its entirety to review and ensure it's doing what I want it to do. To see what else is available through the chat feature, you can type / and review the options. You can use /dev to interact with the Amazon Q developer agent to plan and implement features across multiple files in your codebase. The way it works is you explain the feature you want to develop, and Amazon Q uses the context of your current project to generate an implementation plan and the accompanying code to implement the feature. This can help you build AWS projects or your own applications. You can use /transform to upgrade the language version of your code, like going from Java 8 or Java 11 code to Java 17. Then there is /help to learn more about Amazon Q, and /clear to clear the chat session. So far, we've been using the Amazon Q chat interface to work with existing code, but you can also use it to generate net new code into an existing code base or into a blank file. But instead of doing that here, let's explore how to generate new code using the inline code suggestion feature. I'm going to start with a blank Python file, and I want to create a simple program that creates an S3 bucket given a bucket name. To turn on inline suggestions, I can press the Option C keys.
First, I'm going to type in the import statement at the top of the file, which is importing Boto3, which is the AWS SDK for Python. Then I'm going to make a comment to create the S3 client, and Amazon Q Developer is popping up making a suggestion for creating the client. I can press the Tab button to accept the suggestion, which I will do in this case. Then I want to write a comment describing the function to create the bucket. I will make a comment saying, create a function that inputs a string and creates an S3 bucket with error handling. Amazon Q Developer is making some suggestions, and you can cycle through suggestions using the arrow keys. This way you can see what suggestions are available to you. I am going to select this suggestion and press Tab to insert the code. Now we have a function that will create an S3 bucket given a string as the name, and it will catch an exception and print it so the program doesn't throw a stack trace if something goes wrong. Note how I am writing comments and letting Amazon Q Developer generate suggestions that way. You don't need to use it this way. You can code like you usually do, and it will suggest things along the way. For now, let's continue to use the comment method. Let's write a comment to call the new function, and let Amazon Q generate that as well. Amazon Q put in a placeholder value for the bucket name, but the thing about S3 is that the bucket names have to be globally unique. So I'm going to put in a name here that I think won't be taken. All right, let's run the program to see if the bucket is created. Looks like that ran successfully. Now I want to use Amazon Q to generate some example JSON data, and then I want to write that data into an object in our new S3 bucket. So I will create another comment, and this time I will type generate JSON example data to upload to S3. We can then cycle through the options it supplies us. And I'm going to select this JSON here because it looks fully formed and is a decent example for us to work with. Then I will make another comment to upload this object to S3 by saying upload data to S3. And it has suggested to me a line of code to upload the data to the S3 bucket. I will also now manually add the bucket name that we created earlier. Amazon Q uses information like code snippets, comments, cursor location, and contents from files open in the IDE as inputs to provide code suggestions. So it can actually give you really specific suggestions like this because it takes in all of that context. Now we can go ahead and run the file again. And we don't have any errors here, which means that the bucket was created and the object was uploaded. Now that we have explored how to use comments to generate the suggestions, let's move on to using single-line code completion. Meaning while I am typing, it will make suggestions sort of like a really smart IntelliSense. To highlight this, I am going to add a new function definition to this file. And this time, let's say I want to list buckets. I'll type in def list buckets, and here pops up Amazon Q recommending to me how I can write out the function. I can select the suggestion I want using the arrow keys and press Tab to accept it. So you don't always need to make a comment for Amazon Q Developer to generate suggestions for you. You can just code like normal and it will kick in and start working. Something to note about Amazon Q and generative AI in general is that it doesn't magically know exactly what you're trying to do. Meaning that Amazon Q might not generate exactly what you want every time, but using it can still save tons of time as it can lay out a lot of the basics that you need. Then you can go in and modify it to your specific needs. You own the code that you write and are responsible for it, including any code suggestions provided by Amazon Q. So always review a code suggestion before accepting it, and you can edit it as needed. To get the most out of Amazon Q, you should write comments that are short and map to smaller, discrete tasks so that no single function or code block is too long. Amazon Q is the most helpful when you use intuitive names for various code elements, such as function names. The more code that is available as surrounding context, the better the suggestion will be. To round out this video, let's review why you should use Amazon Q. Amazon Q helps accelerate software development by providing code assistance and suggestions that can reduce total development effort and let you have more time for ideation, complex problem solving, and writing differentiated code. Amazon Q is really great for reducing the amount of time you are spending writing boilerplate code. So that leaves more time for you to focus on more interesting tasks in software development. Amazon Q can field general purpose requests as well as answer AWS API-related coding questions. And Amazon Q can help you improve application security by helping detect and remediate security vulnerabilities. It's important to remember that this is a quickly growing and evolving technology, so you should keep up with the AWS releases to see the latest and greatest features and services in the generative AI space. This was a short demo on Amazon Q, but I hope you can see how it can help you be more productive as a developer. Install the Amazon Q extension in your IDE and sign in with an AWS Builder ID to get started. You've seen how Amazon Q Developer can generate code suggestions, answer technical questions, and help you in your development process in your IDE. But that's not all it can do. It can also scan your code to highlight and define security issues. Amazon Q can scan your codebase to look for security vulnerabilities and code quality issues to improve the security posture of your applications throughout the development cycle. You can run a scan of an entire codebase, analyzing all files in your local project or workspace, or enable auto scans that assess your code as you write it. These scans are powered by security detectors that are informed by years of AWS and Amazon.com security best practices. As security policies are updated and detectors are added, the scans automatically incorporate new detectors to ensure that your code is compliant with the most up-to-date policies. As far as looking for vulnerabilities in your code, Amazon Q identifies various security issues, such as resource leaks, SQL injection, and cross-site scripting. Amazon Q also scans your code and text files for secrets, such as hard-coded passwords, database connection strings, and usernames, as well as can scan your infrastructure as code files to detect misconfiguration, compliance, and security issues. Now let's take a look at some not very secure code that I've written as an example, and let's see if Amazon Q can point out the vulnerabilities in my code. This code is taking in an argument and saving it as a variable called command. Then we are creating a string to be used for the name of a log file. Then I am passing the command and the log file name to a function that will create a subprocess and run the argument passed into the program as a command. If we go look at this function called kickoff subprocess, you can see the line of code where it's creating the subprocess. Then this program is creating a log file with the command that was run. This is already insecure because I'm not doing anything to clean this input before running it as a subprocess. So someone using this program could pass in whatever they want into it to be run. Keep in mind here, I wrote some pretty insecure code on purpose to test the functionality of Amazon Q, but it can help you find a lot less obvious code vulnerabilities as well. Moving along, this program will take that log file and upload it to Amazon S3, which you can see in the function called upload output to S3. Then there is one more function that is making some print statements printing out information about the credentials and configurations being used to communicate with the AWS APIs. This is another red flag. You should never be logging credentials anywhere. I anticipate Amazon Q will flag the few things we pointed out when exploring the code. Let's run a security scan and find out. To run the security scan, I will select Amazon Q in the lower toolbar. Then from the dropdown, I will select Run Project Scan. Now we wait for it to generate the findings. The scan is done running and we can view the findings. I'm going to expand the issues found in this file we're looking at specifically and we can review them. If you double-click on a finding, it will take you to the line it's referring to in the code. The first one I want to review is the hard-coded AWS credentials at the top of the file. This is a big one. You should never embed plain text credentials in your code or log them. So I'm really happy to see Amazon Q calling this out. I can right-click on this and select Explain, which will then ask Amazon Q in the chat panel to explain this finding. Amazon Q then generates an answer to help you understand why hard-coding AWS credentials is a security risk and also gives you some suggestions on how to fix it. You should really use an IAM role or role-based access where you can, or store secrets using services like AWS Secrets Manager. The next finding is regarding the sub-process. You can see Amazon Q found this vulnerability calling out there is a risk for OS command injection. And constructing operating system or shell commands with unsanitized user input can lead to inadvertently running malicious code. That's great. I am glad to see this vulnerability was caught, and it sounds like the fix would be to sanitize the input before just directly running it as a sub-process. Now on to the other findings, which are both referring to resource leaks. To view details on resource leaks, I can right-click and select View Details, where you can then read more about them. Resource leaks mean that allocated resources are not released properly. This can slow down or crash your system. They must be closed along all paths to prevent a resource leak. This finding applies to the lines where I opened up a file but never released that resource. Next, let's review the finding about logging AWS credentials. This one states AWS credentials logged, and doing this could expose credentials to an attacker. So you should encrypt sensitive data, such as credentials, before they are logged to make the code more secure. That was one example of using Amazon Q Developer for security scanning. I would recommend you run a scan on your code before you check it in to help you discover some of those harder to find security issues.